well. And tonight, Ricardo is organizing some students' night out. You might want to join some beach place in São Carlos. Yes, there's a beach bar in São Carlos, believe this or not. And I'll take care of the professors. With a more traditional program, you know, some Italian restaurant, very quiet and so on. But you guys go out. And so, thank you again. And let's move on. For lunch, later on, I'll call the Brazilian students here, those who live in São Carlos, to direct you to different restaurants, because I don't think any restaurant can take 100 people at once. So you have to split in different groups. And I see some faces here that are familiar in São Carlos. So you'll be leading, you know, different groups to different restaurants. So it's my pleasure to introduce Professor John Mikulski. Professor Mikulski is very, very, very well known in the field of mechanical properties of glasses and glass ceramics. Has been a professor at the University of Florida for many, many years. He's still active. It's a real landmark and a role for the younger crowd to see people like Professor Mikulski being active and coming all the way to São Carlos to attend and participate and help us with the lecture. So I think we are about 10 minutes late, which is okay. By Brazilian standards, 10 minutes is nothing. You know, it's within the experimental error. But I'm sure Professor Mikulski will take care of the lecture. Thank you, John. Thank you so
much. Yes, just quickly, someone asked me this morning, am I retired or am I doing research? And answered yes. So he's right. If you're having fun, never stop. So the first speaker is Jose Pedro Reno, and he's going to talk on the basics of molecular dynamics simulation. Please welcome him.
Good morning, everybody. Just a second. Oh, it's okay. That's okay. My name is José Pedro Reno. I am from Federal University of São Carlos, and what I like to do is developing interatomic potential for materials. That's what I have been done for several times. So we can start asking what means molecular dynamics. I'm sure 99.9% here knows what molecular dynamics is. And probably another 80% use molecular dynamics in its research, in one way or the other. But I'm not sure you develop potential for your research. In reality, molecular dynamics has several meanings. Could be real particle motion to be used in spectroscopy. Could be lattice dynamic to measure the vibrational movement of the atoms in the solids. And force field calculation could be quantum mechanical calculation of the structural and individual. Close to me. Oh, shut it down. That's what I'm talking about? Computational of individual movement of atoms and molecules in a model for solid, liquid, glass, granulate system, anything, right? That's what I want to say. Molecular dynamics, in this sense, the computer of individual movement of the atoms. So the essence of molecular dynamics is numerically solve any body problem, or classical or quantum mechanically. Since Newton, any body problem is very important. We want to connect how the collective behavior is related to the single particle dynamics of the system. For instance, the turbulence in the water, how it's connected with the movement in individual atoms in our stream. Okay, so we choose a system. We can characterize this system macroscopically through thermodynamics. You can see color, structure, density, and so on. But we can go inside the problem, the sample, and we can try to describe all the property you can see in terms of individual atoms. Entering the system, we want to see what is made of. Carbon, iron, carbon, silicon, which else? Example. Suppose you have an ideal gas. From the thermodynamic point of view, you have the experimental fact of Boyle's law, Charles' law, Gay-Lussac's law. Everything here is macroscopic. When you go inside the system, we have to ask, is there any mechanical model to describe this kind of gas? So, yes, we can do that. We can know that the particles in the ideal gas is very far apart one of the other. We know that in general there is no collision between particles. If collision happens, it's kind of an elastic shock. So we can create one mechanical model to describe this interaction, just hard sphere. Only when you have particles in this range, you have an elastic shock, otherwise they just go easily, right? So all particles see each other as a hard sphere. Another example, when you go to sodium chloride, for instance, now you have charge transfer between atoms. Coulomb interaction will be essential to do that. It's mandatory. In order to avoid the collapse of the system, you must put some hard sphere, some short-range order to avoid the collapse of the system. Otherwise, sodium and chlorine will collapse. You have to put some interaction. So, depending on the system you are looking at, you have to find out which is the mechanical model you are trying to apply to that system. That's the fundamental idea behind the molecular dynamics. So, this mechanical problem is related to the interaction potential, which are the force between two atoms inside your, your sample. When you talk about interatomic potential, now we have to be more specific. It's just pair interaction. Should I consider three-body interaction? Classical or quantum? Do I have to consider the interaction with the container, the walls of the container? See, the complexity of the system starts to increase when you put some model. The most general formula for interatomic potential is just one body when you have one external field applied, two body, three body, and so on. Right? If there is no external field, you have just this part. Most of the time, the people stop in two-body interaction. Sometimes we need to put three-body. For instance, in semiconductors, silica, for instance, or gallium arsenide system, or something like that, it's mandatory to put a three-body term. In systems with carbon, you have to go to the fourth term, fifth term, to consider the torsion angle and so on. Example, the most simple atomic potential, Lennard-Jones. If you go in the literature, you can see tens of interatomic potential for the most variety of materials. For instance, embedded atom potential is necessary to describe metals. Tersov-Stirling-Weber is very good to describe some semiconductors. Pedone has developed interatomic potential for minerals, a lot of. Brenner and Brenner developed a potential which take into account the change in the carbon, if you sp3 or sp4. And Vashista-Raman is another one. I'm putting Vashista-Raman here because I use this potential, which is very good result. Okay, classical molecular dynamics. If you know potential, I know the energy, I can integrate all the equation of motion, and that's it. Given the potential, I have 3n equation of motion, second order, nonlinear, and this will generate phase space trajectory. That's it. Molecular dynamics, nothing else than obtain phase space trajectory for a bunch of atoms. Classical, okay. Yes, we can use classical simulation. We can compute the de Broglie wavelength, and you know, A is the average distance between particles. When the de Broglie length is the order of the average distance of particles, you have quantum regime. And if it is much smaller, you have a classical one. You can make some small examples. One car with 100 kilometers per hour, one electron, 1% speed of the light, and you see that for the car, lambda is much smaller than the average distance in the street. The distance is meters. This one is 10 to minus 38 meters. It's completely classical. But for electrons, it's almost the same distance. So you have to consider quantum mechanics. By the way, it's not because it's electron which I have to use quantum mechanics. There is a system, a very beautiful system, when you have the helium-4 and you spread electrons on the top of the helium-4. The electron fluctuating on the top of the helium-4. It cannot penetrate in it because helium is a noble material, so Pauli exclusion principle avoids the electron to go inside and fluctuates on the helium. If the density of the electrons is the order 10 to 7 electrons per square centimeter, and you compute the de Broglie wavelengths and the average distance, you can see that this system can be studied using classical dynamics. You can see that this electron in helium form a hexagonal lattice, melts, and so on, right? Okay, this is another ratio of de Broglie and A. You see, for sodium already is almost classical. You can compute that. Okay. all the problem is related to this, which is the mechanical problem. If I know the mechanical model, I can do several things. I will need 3n equation of motion to be solved and 6n initial condition. What we can get solving this stuff? Only phase space trajectory. We are integrating this equation. I have the position of all particles a function of time. I have the momentum of all particles a function of time. That's the only result I have when I solve these equations. So, if I have the interatomic potential, I have the initial condition, and I have some integrator to solve that, I will have all this trajectory of the system. That's the point. What can you get? In principle, everything. If we know the phase space trajectory, the statistical mechanics can give us all the information about the system. That's the beauty of the statistical mechanics. Can measure temperature, pressure, total energy, enthalpy, constant, elastic constants, Book modulus, sound velocity, vibrational density of states, name it. Name it what you want. Because I know the phase space, and I can get everything. To integrate this equation of motion, you can also go to web, ask which one works fine. You can find a lot of stuff. These are all integrators you can find in the literature. In particular, velocity Verlet is very important because they have physical meaning. You know the equation of motion, the Newton's equations, are time invariant. If you change t by t minus t, you have the same result. And Verlet algorithm preserve the phase space volume. So and also you can show that there is physical meaning. So these are just approximation. And of course, this also is approximation, but they have physical meaning behind this algorithm. It's very important. It is just this. I know the equation initial position, initial velocity. I can determine the next position starting from the previous one. Next velocity starting from the previous one. And do this iteratively, you can show you can integrate all the material. Toward the equation of motion, I need 6n equations, initial conditions. For position, we have two ways to do that. Randomly, just put randomly the particles in the box, or starting from the crystalline position for the solid you are studying. For velocity, I can just say all initial velocity is 0, or I can use some Maxwell distribution to get the initial temperature of the system. Doesn't matter. The crystalline position is very interesting because it's very easy. For each kind of structure you have, I know that, for instance, BCC, only 2 atoms per unit cell. So if I know 2 coordinates, I can generate how many size, any size of your simulation box. If you IFSC, 4 atoms per unit cell, so I can just repeat, and I have the amount of atoms to simulate. It's very interesting starting from the let's, because if your interatomic potential is good, this initial condition will stabilize the crystalline phase. If your potential is not appropriate, this crystalline will dissolve as a whole, right? Another important step, time step. When you write the equation of motion, you use the dimensionality, you can see that the time depends on mass of particle, size, and energy. So your time step to solve the equation of motion should be a fraction of this characteristic time. For instance, for argon, this time here is something like 10 to minus 12. So the time step to solve the equation of motion should be of the order 10 to minus 14 seconds. Should be a fraction for that. Otherwise, you don't have the stability of the solution of the equation of the motion. In general, people, including me, use the time step on 1 femtosecond, 10 to minus 15 seconds. You can make a small game. How long you take to follow the system for 1 second? Solve this part here. To do 1 second, I have to do 10 to 15 times this equation of motion. In one workstation, any not very fancy computer, one system with 8,000 atoms, one time step takes 0.026 seconds. If I go to 64 atoms, this is 0.37 seconds. You show that to run 1 second, the first one will take some 1 million years. And if you take the second one, you'll be 11 million years. What am I trying to show here? Molecular dynamics will describe properties in a very short time. You are not allowed to compare with experimental time. The scale of time for experimental is seconds, minutes, maybe hours. In molecular dynamics is picoseconds, nanoseconds, and things like that, right? Are big, very different scale. The beauty of it is that the results are fantastic, right? So, I choose the size of the system. Also is crucial. For instance, why the size of the system is crucial? Because I have to put in the computer, I have to wait time to see the result, right? So I can do that. If you take a diamond has a Wurtzite structure. This is the unit cell, 8 atoms in a unit cell, and the volume of unit cell is 45 angstrom cube. 8,000 atoms is 45 nano cube. 80 million atoms is micron. And if I take 8 to 18 atoms, is millimeter. Again, not only time is very short in the molecular dynamics, but also the system you are studying is very short. You are not able, up to now, to simulate, for instance, 1 centimeter of your material. The record in simulation is Alder and Wright, back in '57. Cadal, 2006, with 320 billion particles. Vashis in 2012 with 218 billion particles. And here in my group, I could simulate 1,340,000 particles. It's very hard. I have to wait something like 15 days to have some result. Mostly because my computer is not as fancy as United States have and things like that. Okay. A little bit more of technical detail. Suppose you want to study the wine. You put the wine in a glass, in a cup. How you make the cup? Metal ceramics, glass, what is that? So how the wine interact with the glass, right? That's important because I want to store wine, but this is in contact with the other part. If you put some particles in a box, the volume goes to L cube. The fraction of particles near the box is something like 1 over L. So, because the number of particles is density volume, I can see that the fraction of particles goes as 1 over cubic root of number of particles. If you are in the real world, you are in the Avogadro number of particles, this is neglectable. You can put inside any kind of container, your result will be about wine. The influence of the container will be very small. But if you have a small number of particles, 10% of the particles are in contact with the container. So you have to take care about that. That is a problem. So I have to eliminate this. To do that, you use periodic boundary condition. And the periodic boundary condition is just you make a replica of your system for all direction, and when one particle leaves the box, one image of that returning that point. Pac-Man uses this kind of stuff to do that. In this way, you eliminate the surface effect. There is no interaction between particles and the border of your system. Right? Of course, if you need some special border, you can do different stuff. For instance, I can use another type of periodic boundary condition. And what I want to say is that periodic boundary condition just eliminate the interaction with the surface. This is not thermodynamic limit. I have read in several places that when you do this kind of periodic boundary condition, you are simulating the thermodynamic limit. That's junk. Nothing to do with that. It's just to remove the position. A little bit more. Potential is known or proposed. I have the algorithm, and how I know the result is correct. How to obtain measurable quantities, such pressure, temperature, energy, and so on. So I have to go to statistical mechanics. Suppose I put one system which is isolated. If the system is isolated, statistical mechanics design in the microcanonical ensemble, energy, number of particles, and volume is constant. Oh, thank you. Thank you. So, I have a lot of constants of motion. Total energy should be constant. Linear momentum of center of mass should be constant. Total angular momentum should be constant. If this is not the case, something is wrong. Statistical mechanics also say that the average, the observable quantity is one average in the distribution. If we assume ergodicity, you can say that this average in the ensemble is just the average in time. So I can do that using the equipartition theorem. The kinetic energy, average, will be the temperature. This is one thing is very nice in simulation, because I can define instantaneous temperature. For each instant I have the temperature, and the total final temperature will be the one average along all the time. And here, temperature against time, the system is isolated, the total energy is constant, but the temperature fluctuates. When the temperature fluctuates, you can see it goes to 325 to 335, oscillating for that. When you put here one straight line, you can see the angular coefficient is 0. This is the final constant average temperature of the system. If you have more complex system, for instance, strontium titanate, you see if the system is equilibrated, all the temperature should be the same. For pressure, you can use the Virial theorem. We can also define instantaneous pressure. You see the result is here. This is one important result we can get, which is the pair correlation function, which is the probability to find one particle if I have someone on the center at one distance r and r plus delta r. The integral, I can count how many particles I have in this small volume here, so I have the coordination number. And the total pair distribution function will be defined as the concentration of each species you have. And this is the result you expect. If you have crystals, we have long range order, and you have very well defined peaks for all distance. This should be the first neighbor, this is the second neighbor, and this in red are the coordination number for materials. If you have temperature in your solid, what happens? You have broadening these peaks due to thermal increase. On the other hand, in the liquid amorphous, we don't have long range order. Only the first short order is preserved, and suddenly, very short distance, the order disappears. There is no order. In the gas, it's completely chaos. So you have. Why the partial is important? Partial is important because it then can give you much more information of the structure of the system. They can say how the total G of R coming from, which pair of interaction is responsible for that peak in G of R, right? We can see that the coordination number very well defined. This is one example, silicon carbide, the total G of R, the first peak happens about 2 angstrom. And you see that only the contribution of silicon carbide will contribute to the first peak. Silicon, and carbon are not responsible for the first one. So the partial allow me to follow which one of these correlations are involved here. This is for a crystal, and this is for amorphous, the same stuff. This is another example for other systems. Three-body correlation is very important. If I know this AB vector, if I know this AC vector, I can compute this angle using the dot product of the system. Very easy. Here one example. Zinc telluride, under pressure. The system is in zinc blend. I start to increase the pressure, now increase, and suddenly the system suffer one structural phase transformation going to rock salt structure. How can I know this is the rock salt structure? I can go to the pair distribution function, and you see that up to 10 GPa, the first peak decreases. You are putting pressure, the system is become denser, and when we cross some value, the green, the distance between zinc tellurium increase, showing that something happens. When you compute the bond angle distribution, you see that before is a zinc blend, that means the angle is internal 109 here, and at 12 you have two peaks, 90 and 180, which is typical of rock salt structure. You can follow all this stuff. Experimentally, you know the structure of material doing diffraction experiment. X-ray, neutron, anyone. You just, through some radiation, you observe the intensity of the scattering light. And S of Q is the static structure factor of your experiment. And it is related to pair distribution function. In general, all the experimental results occurs in the reciprocal space. You measure frequency in a Raman, you measure Q value in scattering experiment. On the other hand, molecular dynamics works in the real space. You measure time, you measure distance, you measure GFR. The connection between experimental MD is a Fourier transform between these two guys. And your atomic potential will be good if you can describe your system very well. If the molecular dynamics and the neutron reproduce well of your system. This is mandatory. This is another example. Dynamical property, mean square displacement, Einstein relation for diffusion, and I can see mean square displacement. This is a result for the diffusion of silver in this super ionic material. Velocity-velocity autocorrelation function is a single particle correlation, and you can see that if I know Z, velocity-velocity autocorrelation, I can compute vibrational density of states for the system as a whole. This is one example for indium phosphide, and this is the Fourier transform of this function to this one here, showing the agreement is very good. This guy, Brenner, wrote this paper. A good interatomic potential must be flexible, able to describe several properties of the system, accurate, reproduce data appropriately, transferable, describe other properties not used to parameterize the interatomic potential. And you can obtain the result in a relatively small time. It should be computational efficient as a whole. This is the main objective when you propose one interatomic potential. You have to follow this to show your potential is quite good. Okay. Not only the system isolated, but I can use canonical, isobaric, isothermal, grand canonical, charge variable. This is interesting because I can compute chemical reaction for this. I can use for non-equilibrium molecular dynamics, planar shock wave, projectile impact, granular media. And molecular dynamics has been used in all areas of the science. It's fantastic. It's really very, very powerful technique. Go to the commercial problem, you can see lots of potential programs to do the molecular dynamics. In particular, lamps from the Sandia, in my opinion, one of the best at the moment. It's very powerful, very robust, very easy to use. Example, project impacto. This is just a toy model. I have one block of Leonard Jones material, and the projectile is also Leonard Jones. It's a high impact. No? You see that the system destroy. If the velocity is very high, what happened? This is high speed, low speed. If it's low speed, it's interesting because the projectile amorphizes and they start to recrystallize in the same structure of your target. You have seen the same structure here. This is a toy. This one result, Zanotto and Leila and myself, we study. When you start from the liquid, you go to supercooled liquid. This supercooled liquid could or crystallize or become anamorphous. So that's it. This is zinc selenide material, where you have a melting, and when you go, you have supercooled liquid, and you have two regions, very deep supercooled and very high supercooled limit. Here in this part, we can observe spontaneous crystallization of your system. And this is a snapshot of the system at 3 different temperatures following the time. At 900K, you start to see some small group of atoms, and this small group of atoms grows, and you have a crystallization of material. When you have higher temperature, the first nuclei will appear much later on the time, and you can follow that. Right? We did for 15 samples, and because the nucleation happens randomly, each one here is that some sample will show initiation of the crystallization much later on time. This is one example of the liquid. Orange is wurtzite, blue is zinc blend, and you can see that some group of atoms do not reach the critical volume and dissolve, and suddenly they have the critical size, and you have a crystallization as a whole, right? Okay. You can go further, closer to the system. You can describe now the effect of electrons, the electronic DFT calculation. And today, you are talking about machine learning, including all this stuff together. I am a completely analphabet of machine learning. I will be quiet. Pedonio will talk about that later. So, moral of story. Archimedes, very long time ago, say that, give me a lever, and of course 1 point of support, and I'll leave the world. I can paraphrase this guy and say, give me the interatomic potential, and I will give all the answer you want, right? That's the point. I want to thank our funding agency and the collaborations I have been using Zanotto, Leila, and a lot of other people. I guess I can stop here.
All right, we're open for questions. It's a wonderful talk.
Thank you for a great talk. Could you elaborate more on what the benefits of increasing your simulation size is, going from like 8,000 to 16,000 atoms, as well as like what is the scaling of that? Do you see the same benefit going from 8,000 to 16,000 to 32,000, or is there kind of a decreasing benefit?
Depending on the property you want to see. In general, systems with 8,000, 64,000 particles, normal temperature, pressure works fine. But some property, for instance, crack propagation, you need much more particles. So a small one, there's no way, right? Depends on what kind of information you are looking for.
It would be nice if when you ask a question, please, introduce yourself. So we don't know yet, we did not memorize yet all the names and faces. So please say your name and where you're from. Thank you.
Thanks for your nice talk. My name is Rui Hongcao. I'm a PhD student from Otto Schott Institute of Materials Research, Yale University. And I have a question, like how to describe the thermal driven ion changing process between the glass and the molten liquid melts, and which theory could describe this dynamic diffusion process?
I could not understand what you said.
Okay, so my question is like how to describe the thermal driven ion change process of the glass when glass is put in the liquid melts for the ion change. Yeah, ion change. Which theory could describe this process? Like, yeah.
Oh, okay. No, see, you have a liquid, right?
Yeah.
You have a potential for this liquid. Water. Now you have a glass. Mm-hmm. You must find one potential with the interaction between water and glass. It's fundamental. If you don't have one mechanical model to describe this interaction, you are not able. You have to propose that. So we can, let's simplify. My glass is water glass. You cool it down and make one wall of glass made by water. So I can use the same potential of this wall glass water with the water here, so now I can do this stuff.
Yes, I mean, is there any theory developed to describe this dynamic process?
Well, all problem of molecular dynamics is find the mechanical property you are to describe that system. That's the big deal. I must have the interatomic potential. If you don't have, forget. Go sleep and don't work.
Next question. No.
My name is Rachel. I'm from the Catholic University of America in Washington, D.C. And my research is with fracture and molecular dynamics. I'm just starting to do molecular dynamics. So I was wondering what potential you would suggest for crack propagation in glass, specifically silica.
You know, there is no one potential for general, right? Only God knows which is the potential of everything. Yeah. Each kind of material you have to find the best one. There's no way. All the materials I have been studying, I'm using Wachista potential. They are ionic, and I know how to parameterize it, right? It works for all the semiconductors, works for lead titanate, strontium titanate, magnesium silicate, everything I know how to do that. Pedonium has a bunch of potential for minerals in general, right? And works. So depending on material you are. Silica glass also, pure silica. This was my second paper was studying silica. I used Wachista potential. I have heard about some complaint about that because the density when you have the glass is not the experimental one, but the structure, the effect of pressure on that works very, very well. Maybe you have to redo Wachista potential for another stuff. Wachista potential works very fine.
Thank you.
I will use the prerogative of being session chair to follow up on that. I loved your last slide with saying that if you could select the correct potential, and problem is over. In selecting a potential, you usually try to match it against experiment.
Yes.
However, my experience, very limited experience, is that you have to select the experiment in which you match. And in general, one potential will not match all the experiments. So you have to decide what is the most important. How do you decide?
Wachista potential consists of Coulomb interaction due to the charge transfer, charge-induced dipole due to the electronic polarizability of the atoms, one steric repulsion to avoid the collapse, and dispersion term, van der Waals, 1/R6. That's the idea, right? When you analyze this potential, you can see that the steric repulsion, who takes care of the steric repulsion? What is the influence of the steric repulsion in your system? When you have bulk modulus means how easy or hard to change the volume with the pressure. This relates to the steric repulsion. So the term for steric repulsion, I use bulk modulus, right? Charge, you can see that the charge in Wachista potential scale all the potential. So the charge square in reality, is a scale of energy. So the cohesive energy of experimental will give me the charge of the simulation, right? And then I use another information, for instance, C11 elastic constant to see what happens. So I can take energy, length, pressure, and length scale. If I fix this, I can obtain other parts.
Yeah. All right. One of the things we found in fracture is that once you get a potential for the original system and it breaks, you have to change the potential because after it fractures, you no longer have the original structure and the structure has changed.
I never did the fracture myself, But when I was in Vashista group, they was using to study the fracture in aluminum nitride. They have a sheet of material and pull it in order to crack propagate. And they didn't change the potential.
All right, we are ready for the next talk. Where do I have them? Thank you so much. What happened to my, book? All right, the next speaker is Alfonso Pedoni, is that right? University of Modena and Reggio Emilia. And he will be talking on machine learning potentials and glass simulation.
Thank you. Just a moment. Yeah. Okay. Okay, so good morning to everyone. Before starting, I would like to thank the organizer, especially Edgar and also Eric for the support and for the kind invitation and for the economical support here. As you can infer from the title of my presentation, today I would like to talk about machine learning potentials. There is also glass simulations, but I will essentially focus on machine learning potential because nowadays these are tools which are very innovative and important in our community, I think. But there is a lot of work to do on it. So this is the outline of my talk. So I will start by trying to answer to these questions, why modeling glass is so difficult, because it's very difficult. Then I will talk about the challenges in developing interatomic potential models, and I will go toward machine learning potentials. I will try to explain you briefly and in a simpler way several frameworks that are used nowadays, also in my group. When you talk about machine learning potential, you have to talk about the critical role of the dataset. So I will touch also this problem, and then I will show briefly several case studies that we have investigated in our group on silicates, aluminum silicates, sulfides, and oxysulfides glasses. And I will show you the accuracy that can be reached with machine learning potentials in several properties. And then I will conclude. So I don't know if I will be in time because I have a lot of slides, but I will try to do my best. So let's start from a very fundamental question. Why modeling glass is so difficult? So the reasons is essentially that glasses are metastable, non-equilibrium materials. They are metastable materials. So their properties, the structure and properties of glasses strongly depends on the way in which these glasses are formed. So especially the cooling or the cooling rates. So if we cool a glass with a very high cooling rate, we don't give the time to the system to relax. So it gets trapped in high energy local minima in a very complex potential energy surface. If we cool the glass slowly, we give the time to the particles to overcome barriers and so to explore the potential energy surface and to find local minima with low energy. The problem in molecular dynamics simulations is that the time scale that we can assess is much, as Rino told us before, is much less than the experimental one. So we can run simulations for a few nanoseconds, and this leads to the employment of cooling rates which are up to 10 orders of magnitudes higher than the experimental ones. So with MD simulations, we are here. With experiments, we are here. So there is a huge time scale gap. So when we generate a glass with MD simulation, we generate what we could call a fast quench system, which is much more disordered than the experimental glasses, and also the properties can change a lot. So in the years, there have been several studies, several MD simulation studies in which they have compared the effect, they have investigated the effect of the quenching rate on several properties. Here I have just summarized some plots taken from recent literature from different groups. I just want to highlight that the cooling rate has a different effects depending on the glass composition that we are using, for example, that we are investigating. For example, here this is the CTE for sodium silicates, this one, and for silica, you see that the effect of the cooling rate is really different, and also QN distribution here. So, and also the effect is also different with depending on the properties. So this is a huge problem that we have when we try to model these systems and to develop interatomic potential. So let's go to the other challenge, the one that I'm trying to tackle in my group. So the challenge is how we can develop reliable interatomic potential. Which are the challenges? Which are the difficulties? Essentially, developing an interatomic potential for glasses is much more difficult than for crystals. With crystal, we are in a comfortable situation because we have a unique crystalline structure. So we have unique properties. We have lattice parameters, we have positions, and we have several properties. So we can directly fit on experimental data or to perform DFT calculations of these properties and to fit it directly. With glasses, the situation is different because we don't have a reliable and unique structure of a glass. So glasses are described by ensemble features, ensemble structural features. So we can know the correlation functions, as we saw before, the distribution of bonds and distances, angles, distribution of medium range order. We can have neutron diffractions and so on, NMR spectra, so properties like this. But these properties are not unique. I mean, these are average properties. And another important point is that these properties depends on the cooling rate. And when we generate a glass, as I said before, we use very fast cooling rates. So there is a mismatch between our cooling rate to generate the glass and the experimental data that we can use to fit interatomic potential. So another problem is a mathematical one, which is related to the cost function. When we fit an interatomic potential, when we want to optimize the parameters of an interatomic potential, we have to build a cost function or a target function that gives us this is essentially a simple form is a sum of square of the difference between the observable that we want to fit and the observable that we compute with our simulations. And if we use different observables and we have an interatomic potential with different parameters, the landscape of this cost function is really complex. So we have several minima, like in the potential energy surface of glass materials. So when we start from an initial set of parameters, even in this case, it is very simple to reach the first minimum. So it is difficult to obtain the optimal parameter set for a force field. Even if nowadays there are several machine learning or several global optimization methods to explore a wide range of a landscape or of a function that can help, but the problem is still difficult. I mean, so let's see. So, historically, especially in my group, we decided at the beginning to develop interatomic potentials for glasses, starting from crystalline materials. So I developed a set of interatomic potential, which is quite simple, to several oxide systems. The problem with this approach is that we are sampling just a small portion of the potential energy surface, because we fit parameters in a global minimum of the potential energy surface, which is the one of the crystalline phases that we are using. But glasses can expand a wide range of these potential energy surface. So when we melt the system and we perform MD simulations of the glass or for a melt, and then we quench and so on, we are exploring a portion of the potential energy surface which has not been included into the training. So we are essentially extrapolating, okay, outside of our domain. And this can be a problem, even if this way of developing interatomic potential has been successful, because the glass properties that we can get with this set of potential is quite good. So another approach could be the one that I have included here. So empirical potential structure refinement. We can fit directly the parameters of a force field against experimental data. So for example, neutron diffractions experiments or NMR, so with using Monte Carlo algorithm to optimize the parameter. The problem in this approach, in this approach we are fitting directly on glass property and glass structure, but the problem here is that this approach strongly relies on the availability of experimental data. And if we want to study new glass composition, we want to have interatomic potential for new glass compositions for which there are not experimental data, this approach is not appropriate. So we want to go towards a way of fitting interatomic potential without using experimental data. So what we could do is to sample the potential energy surface of our complex system using DFT calculation, so ab initio MD simulation that can be coupled also with enhanced sampling methods like metadynamics or stuff like this that helps you to explore, to overcome energy barriers and to explore the whole potential energy surface. So the idea is let's use ab initio MD and enhanced sampling to explore these complex potential energy surface, extract configuration, and compute at the DFT level energy forces and stresses, and fit directly against these properties. We can do it with empirical potential, yes, but the problem is that it's a mathematical problem. So empirical potential are good because are based on physics, so we understand, we can interpret them, we understand them, but they don't have the necessary flexibility to reproduce all these properties with the small error. So here it is where machine learning comes in. So machine learning methods can be of huge help because they have a very high mathematical flexibility. So now I want to discuss a little bit about the different frameworks that we have, that we can use. So essentially, in machine learning interatomic potential, we assume that the total energy of our system is given by the sum of local atomic energy. So we assign an energy to each atom of our system. And the energy, the local energy of an atom, which is represented here with the blue here, strongly depends, it depends in a very complex way on the local environment of each atom, which is described by a descriptor, usually, or a functional basis, so the vector qi here. And we can have different representation of our local atomic environment. We can have atomic symmetry function, the SOAP descriptor, the atomic cluster expansion, and we can also describe this local environment as a graph. So depending on the representation of our local environment and depending on the machine learning methods that we use to map a local environment to the site energy, we can have different machine learning interatomic potential frameworks. So we can have neural network-based machine learning potentials or kernel-based machine learning potentials, okay? So now I will try to show you, to explain you briefly some of these frameworks. So, the first thing that I would like to say that you can heard about invariant or equivariant models. In our case, when we want to reproduce the energy, we know that the energy is invariant with respect to symmetry transformation, with respect to translation of a molecule, or a rotation of a molecule, or the permutation of the atom inside the molecule of your system. So our model, when we want to predict the energy or scalar quantity, so like site energy, atomic energy, chemical shielding, and so on, we must use an invariant model. So if we transform the input, the features, input, the output must be invariant. It doesn't have to change, okay? This is an invariant model. When we want to reproduce, we want to predict tensorial or vectorial properties, we have to use an equivariant model. So let's think about a dipole moment of a molecule. If we rotate the molecule, so if we rotate the reference system of the molecule, the dipole moment change, its orientation change, okay? And it must change in the correct way. So it must be, we say, equivariant with respect to input, the transformation that we apply to the input features, okay? Usually it is a combination, a linear combination of the features. So this is just because in the next slide I can talk about equivariant input. So, okay, so let's start with the first. The first machine learning potential was developed by Michele Parinello and Georg Berer in 2007. This was based on a local descriptor which are called atomic symmetry functions, which are functions of this type. You have a summation for the radial part. We have a summation of Gaussian functions, which are multiplied by a smoothing functions to have a continuous. We must have a energy must be continuous, and must also the first derivative and the second derivative must be continuous. So we have to apply a smooth function. Essentially, what we do with this symmetry function is that we project the distances between atoms and the angles between atoms on these symmetry functions. So in this plot here, we have how these radial symmetry functions varies depending on the parameter eta here. And here, as it varies depending on the parameter RS. So here, usually what we do is to generate a mesh of point of this parameter, eta and RS. So the finer is the mesh, the better you describe your local environment, okay? So at the end, we take the distances and the angles, okay? Different, we have, for example, for one pairs of atoms, we have a distance, and depending on how many symmetry function we employ, we have a set of numbers that we concatenate in a vector, which are the features that we use to feed the machine learning model, okay? And this feature must be invariant with respect to translation, rotation, and permutation of atoms. So then we have a neural network algorithm that takes these inputs and maps these local environments to a local site energy. Then you sum all the atomic energies and you get the total energy of your system. This is the high-dimensional neural network machine learning potential that was developed by Michele Parinello and Bere. I don't know if I have to explain a little bit about how neural network works. Essentially, I try to be very quick. We have a set of layers. Every layer has several nodes. So what happens for each node? In each node, we have some inputs, a certain number of inputs, which are weighted, that comes from the input or from a previous node. And then we have several outputs. So each node take this input and apply a linear transformation. This one, it's a linear transformation. We have several weights, which are the parameters of our neural network. And then it sum all these linear transformation and apply an activation functions, which is the functions that gives nonlinearity to the model, okay? So we have several layers. This is the case of one needle layers. And so we map an input to an output. These tools are really powerful, depending on the number of layers, the number of nodes we use. We can reproduce any mathematical functions of any complexity, okay? But we lose the interpretability of the model, so this is the problem. Okay, so the next descriptor, which is really used, are the smooth overlap of atomic position descriptors, which is called SOAP. Here what we do is we take a bunch of atoms. We want to describe the local environment of each atoms. So we build a smooth atomic density by putting Gaussian with different standard deviations to nuclei positions. Okay, so we have a local density, and then we expand this local density using a basis set. And as a basis set, we use radial basis, like the one that you use when you solve the Schrödinger equation for hydrogenionic atoms, and spherical harmonics, which have the rotational symmetries with them, which is described by the L and M quantum numbers. So we decompose these local energies with these functional bases, and you get coefficients of this expansion, C, which is labeled with different quantum numbers. I don't want to focus on these indices because it's a mess, actually, and I don't want to confuse you more. So you get these coefficients, and these coefficients includes the physical information about your local environment, okay? These coefficients must be invariant, so there is a transformation here, you have a summation on M, and you get this descriptor, which is invariant and doesn't depend on the rotation of your molecule. So actually, this is the input. It's a vector containing numbers, essentially, okay, which have a meaning. So this these basis functions has been used in the Gaussian approximation potentials, which have been developed by Gabor Ksani. Also, the SOAP descriptor was proposed by Gabor's group. So here, what we do, we have a bunch of reference configurations that we take as a reference, and using a kernel function, and this kernel function here will be a Gaussian kernel function, we estimate the potential energy surface as a basis of these kernel functions that measure the similarity between your new configuration, the one that you want to predict the energy, with the configuration that you have in your data set, okay? So to explain it in a simple way, this is similar to kernel ridge regression when the kernel is a Gaussian function. So you have a function here, and you expand these functions as a combination of Gaussian, essentially, okay? It's a little bit more difficult, but to make it simpler, this is what you do. But with the Gaussian process regression, the powerful of these methods is that we have an estimate of the average value of the function that we are reproducing, and also the uncertainty associated to each point. So, for example, if you look at this plot here, if these are the points that we know, because we have it in the dataset, here the uncertainty is very small, it's 0. But if we go here in this region where we don't know, we don't have references, the uncertainty, which is represented by the gray region, is very large, okay? So when we run a gap potential, we can know if we are exploring a point of the potential energy surface which is far from our reference data set, okay? This is an important point of these models. So DeepMD. DeepMD is another machine learning potential. It's an end-to-end machine learning potential. End-to-end means that you don't have to worry about the optimization of the local descriptor, something that you have to do with the previous methods. So the code just takes the Cartesian coordinates of your system, and it generates the local descriptor. Let's see how it works. So you have the coordinate matrix. From the coordinate matrix, you can generate a local environmental matrix. I will show you later. Then you have a neural network that is called embedding, because it takes the coordinates and transforms the coordinates in the local descriptor, in the features that are taken from a fitting neural network, and you map the descriptor to the local energy, and you sum all the local energies. So here we have two neural networks, one to create the descriptor and the other one to map the descriptor to the local energy. So we have two sets of parameter weights of these networks, which must be optimized by training. And we optimize them by minimizing a loss function of this type. And here you can see we use energies. Usually we use root mean square error on the energies, forces on atoms, and also virials. You can also use virials. So I don't want to go into the detail. There are several, these errors are weighted. So there are some weights that vary during the training, they varies. Let's skip this. So I want to show just this descriptor here. So you have an atom, you use a cutoff. So you take all the atoms around and within this cutoff. You generate for each atom I, you have a set of, you have a matrix with all the x, y, zeta coordinates for each neighboring atoms around. But the problem with this representation is that it's not invariant with respect to rotation and translation. So the first thing that you do is to compute the difference between the position of the nuclei J with the central nucleus. So this matrix becomes invariant, translational invariant. We want it to be continuous with respect to R and with respect to the derivative. So we must multiply these elements for a smoothing function so that the energy is continuous. And then we generate these elements of the matrix by dividing by R. In this way, we weight the most the atoms which are closer to the central atom. So at the end, we have this matrix, which is called local environmental matrix for each atom, in which we have several columns. In the first columns, we have a radial information, and in these, the other three columns, we have the angular information. Okay. And this describes the local environments. The problem of this representation is that it's not rotational and permutational invariant. So there are some operations that must be done on it. Okay. These things are quite, complex. It can be quite abstract, but have been demonstrated in the original papers. So what DeepMD does is it takes the first column of this matrix and uses a neural network to generate what is called an embedding matrix, which is this one here. So it multiplies the local matrix for its transport. This multiplication leads to a rotational invariant descriptor. To make it permutational invariant, you have to multiply to the, I don't know, it's not working anymore, to multiply for these two matrices here, which are generated using a neural network, okay? So this process is done during training of your model, so you don't see it, actually. So the problem with the machine learning potential that we have seen up to now is that we have to train a machine learning model for every pairs of species that you have in your system. Okay? So if you have just a monatomic system, just carbon, for example, you just have to optimize one neural network. Okay? But if you have a system with more elements, for example, silicon, sodium, oxygen, you have 9 pairs. So you don't have one network, you have to train 9 networks. Okay? And this is expensive from a computational point of view, because depending on the number of species that you have in your system, the cost of the calculation increases as the square of this number, okay? So we have a combinational explosion with the multiple species. So how we can solve this? In the last years, this has been solved by using what it is called chemical embedding. To make it very simple, what chemical embedding does, it takes the atomic number of the atom, and with the machine learning model, it maps it to a vector of numbers, okay? these vectors are generating during training using a very large data set. So you have an actor, an embedding vector that describes the chemistry of your element. And it has been shown that if you plot these vectors, this point in a space, they are connected as in the periodic tables. So there are several papers. I forgot to put the reference here, but there are several papers showing this. So in the DeepMD, what you do, when you generate the embedding network, you take this vector and you take this column of the local environmental matrix and you generate the embedding matrix. And so in this way, you just have to train one neural network, okay? Okay, so another very important descriptor or basis is ACE, Atomic Cluster Expansion Descriptor. This is a complete basis set that includes, has been demonstrated that it includes all the descriptors that we have seen, so SOAP and atomic symmetry functions and also other descriptors that I haven't reported here. What ACE does, essentially, we assume that the local environment of each atom is a star graph, okay? So we have several neighbors. So we have several nodes with every node has its characteristics, chemical characteristics. And then we generate a particle basis set. So for each atom, we compute a basis using always spherical harmonics and radial basis, as for hydrogen atoms. So in this way, we know the spatial arrangement of atom J around atom I, okay? Then what this descriptor does, it computes what is called atomic basis. So to make this descriptor permutational invariant, it does a summation along all the surrounding atoms of this of this particle basis, and this makes the descriptor permutational invariant. Then there is this operation is very important because gives the high order to this descriptor. It's a product of these bases because these bases are two-body orders. So it takes into account the interaction between only two atoms, pairs of atoms. By doing this tensoral product here, up to an order nu, we can have a many-body order descriptor, which gives the powerful to this descriptor. And then you symmetrize these product bases using Clebsch-Gordon coefficients. So you have a basis set that is equivariant, okay? Can be used to predict energy, but also vectorial and tensorial properties. Yeah, I know it's quite difficult, but once you have this descriptor, you can get the invariant elements of the B basis, and with a linear combination, you can compute the local energy and the total energy. And the results on the mean of the root mean square error are quite good compared to other machine learning potential. I will skip Grace. Okay, so MACE is one of the tools that we are using the most in our group. It combines message passing neural network with the atomic cluster expansion descriptor that we have just seen. And is powerful is that has been trained. There are several models, pre-training models, which have been training on several quantum mechanical dataset. So this is the scheme of message passing neural network. Essentially, we describe the local environment as a graph. Each node has one feature vector. Here, the feature at the beginning, the color is the same because these numbers describe the the species, I mean the chemical species, without any information from the neighboring atoms. So we have this situation here. In a message passing neural network scheme, what happens is that every atom has its own characteristic. You compute a message, it can pass a message to the central atom, okay? So at the first round, as you can see, for the first layer, for example, a few orange elements passed from the atom 2 to atom 1, and a few yellow here. So with the first layer, the first iteration, atom 3, atom 2 pass a message to atom 1. Okay, so its feature vector changes depending on this message. And in the second iteration, you see that here we also have a green element, meaning that in the second message passing, some information from the second coordination sphere goes to the central atom. So varying the number of layers of message passing, you can pass information to the different nodes and take into account also larger interactions. So Maze essentially uses uses the atomic cluster expansion descriptor to generate the message. I will skip all these things here. What it is important here that you can find a lot of foundational model which has been training on several data sets. Okay. And you can also fine-tune them. So you can take the original data set, generate a replay set, you can generate your own data set, and you can combine them to fine-tune the model to make it more specific to your particular problem, okay? And this is what we are doing in our group for glasses, essentially. Okay, so let's go to the data set, the problem of the data set. So all these models are essentially, all machine learning models essentially are not extrapolative models, okay? So the results of your machine learning potential or your machine learning model strongly depends on the data set that you are using to train it, okay? So it is, in my opinion, really needed to know exactly how your data set is built, what it contains, so that you can know how your machine learning model can perform on a particular system, okay? So we want to generate a machine learning potential that must be accurate, it must be robust, and transferable to different systems. And so for glasses, the generation of a data set is quite tricky because you know, the accuracy strongly depends on the level of theory of the quantum mechanical calculation that you are using. So if you are using a quantum mechanical method that is not able to reproduce well your properties, you can forget about the accuracy of your machine learning models because it just replay the DFT data. I mean, so if they are wrong, your model will be wrong, okay? So the accuracy depends on the level of theory of quantum mechanical calculations. The robustness and transferability depends on how you sample the potential energy surface. So for example, in this example here, you see in this region here, you don't have a point. So it means that whereas your potential perform really well in this region, if your system fall in this domain, it is guessing. So your results can be completely wrong. In most of the time, your simulation stop, crashes. So what happens usually? You run a simulation at a certain point, it crashes, okay? With empirical potential, this doesn't happen. Okay, but with machine learning, it happens a lot. So you are guessing here, so your results here can be completely wrong. So how we must sample this potential energy surface? For glasses, the sampling is quite tricky because if you want to generate a machine learning potential transferable for different elements, we know that in glasses we can combine different elements. We have a multi-component systems, and we can have a very complex chemical disorder around each ion. So silicon, oxygen, silicon, silicon, oxygen, boron, silicon, oxygen, aluminum. We can have different QN distribution. How many aluminum are around one silicon? So it's a mess, essentially, okay? So, and if your model doesn't know in the data set all the kind of chemical disorder that every atom can have, you can have very strange results. So the first thing that I try to teach to my student, you have to know everything about your data set first, okay? The other problem that we have is that we want to melt the system, high temperature, and then we quench. Oh, sorry, I'm not used to. So you have to melt your system and then quench. At high temperature, the configurations of each atom is quite distorted. Okay, so you have to take into account also this. And this depends, and the robustness and transferability depends on how you sample the potential energy surface. Okay, so to show you what I mean when I say the accuracy depends on the data set or the level of theory, here is an example of the reproduction of the density with a model training on PBE. You see the density of sodium silicate is heavily underestimated with PBE. This is also for other systems, chlorine, doped lithium borosilicates. Okay. So if you improve your DFT calculations, for example, adding the D3 Grimm dispersion corrections, you see that you reproduce much better the density of your system, of your glasses, and also of crystal. This is a sodium silicate. When you use PBE plus D3, you have much better results. Okay. So also for aluminum silicates, here we have a albite, anortite, plagioclase glass series. And if we look at the mean absolute error, we see that if we take PBE, a model training on PBE, we add the D3, we have the error half. And also PBE sol, which has been developed for solids, provides much better results. So the accuracy strongly depends on the functionals that you are using to generate the data set. So sodium silicate glasses, here I will try to be fast here. I don't know how much time do I have? 10 minutes? Okay. So here, just to show you that how we can analyze our data set. Here, for example, we have generated a data set varying sodium composition from 0 to 50%. We perform several MD simulations at different temperature. We extract configurations, and we compute energy forces and variance. So we have our data set. And here you can have a plot of the distribution of silicon-oxygen bonds with silicon angles, QN distribution. So, for example, in this data set, we have a lot of Q2, Q3, Q4 species, while we don't have Q0 species because we generated a data set with up to 50% of sodium. So this data set, or this machine learning potential, I don't know if it can be used for inverted glasses in which you have more than 50% of sodium oxide, okay? So look at your data set first. So for example, we don't have 3 bridging oxygens here, okay? We don't have we don't have free oxygens. So this means that we cannot safely use this potential if in our system we know that there are 3 bridging oxygens, okay? This is very important. Okay, this just to show you the accuracy that we can reach with machine learning potentials. We can have mean absolute error of the order of milli EV per atom on the energy, and 0.1 EV for forces. Okay, you cannot reach this value with empirical potential, I'm sure. So these are some, you can compute obviously the several properties. Here we have the structure factors for sodium silicate and for silica. What I wanted to show you here is the effect of the dispersion interaction. If you see, the dispersion interactions have an effect on the medium range order, so they vary the first peak in the structure factor. And including these interactions improves the description of your system, your class. Okay, no, I will skip this. I just want to, okay, this is another important point. QN distribution, we know that with empirical potential, especially when we use rigid ionic model, we are not able to reproduce well the QN distribution. So this is with the Schick potential, BMP potential, our new version of potentials, machine learning potentials provides the better results, even if they are not perfect, but they provide better results here in these systems. Okay, a property that really improves with machine learning potential is the vibrational density of states. Here you see that with machine learning potential, the red curves, you reproduce much better the vibrational density of states of silica and sodium silicates compared to the empirical potential. Here are some coefficient of thermal expansion. You see that the machine learning potential is better than BMP and Schick here for sodium silicates. And this is for mechanical properties. Here we see that our model, in this case for the Young modulus, reproduce better the Young modulus here. We still have problems. In this case, the MACE model has not been fine-tuned, so this is the reason why it doesn't perform well. So a problem that we have and that we would like to stress is the middle range order. With machine learning potential, we are facing a problem of reproducing the medium range order. This is an example for sulfide and oxysulfide glasses. It's in collaboration with Professor Steve Martins. I don't have time, I guess, to tell the complete story, but I will show you just a few results on this glass series in which we replace sulfur with oxygen. What happens? The properties, experiments show that the properties strongly relates with are strongly nonlinear. We have a strong nonlinear variation. These nonlinear variations strongly depends on the complexity of the structure. We can have P0, P1, P2 species with different degree of oxygen and sulfur, which are really complex. This is the variation of non-bridging sulfur, non-bridging oxygen, bridging, bridging sulfur, bridging oxygens. These are experimental data, okay? This shows that when you replace sulfur with oxygen, the replacement is not random. So oxygen prefers to go in a bridging position, okay? And this shows that what happens for the phosphorus. We have a disproportional reaction. We have used several machine learning potential training on a very different data set. The outcome is that the short range order is well reproduced. But if we go, I skip this, but if we go to this speciation, you see that with the foundational model, the trend is completely wrong because we don't have the crossing here. Experimentally, the crossing should be here. With the machine learning potential, the foundational model, the crossing is beyond 3.5. When we fine-tune the model, we improve it. It's not perfect, we are improving. These are the PN speciation. You see the trend is completely wrong. Here, we improve a little bit, but we are still far from the experimental data. Okay, this is an important point. Overall, the structure is well reproduced because we see that oxygen prefers to go in bridging position. So with the substitution of sulfur with oxygen, we have the formation of chains, longer chains in these systems. So the properties change. These are the mean square displacement. Here I just want to go toward the last slide because there is Phil here. I want to show him the results. So Phil is working a lot on the effect of pressure on the structural properties of glasses. And here in particular, I want to show how our machine learning potential reproduce the variation of the aluminum coordination with pressure. This is BMP, so all the empirical potential are not able to reproduce the jump that we have experimentally here when we have 6 gigapascal. With the machine learning potential, we improve the situation. We are not reaching the right results, but we are improving. So with MATPES, I guess, yes, MATPES MACE, this should be, I don't see, MATPES, it should be this one. We are reaching the experimental data. So, but we have to work on it. Okay, so in conclusion, I hope I've shown to you that machine learning potentials provide quantum mechanical accuracy in a fraction of computational time. The accuracy of the machine learning potential depends on the level of theory used to train it, to generate the data set. Pre-trained foundational models are good starting point, but must be fine-tuned. And there are several open challenges. The medium range orders is one of them. And so thank you to all of you for being here.
And don't forget to say your name before you ask the question. You have one? Yes.
Hi, this is Rachel from Catholic University in the United States. I have a lot of questions, but one of them is, do you think that the medium range order is not well reproduced because of the limitations of DFT and the system size that you can get with that?
Yeah, this is a very good question. There are a lot of possibility. One is the level of theory. The data set, we are working on it, trying to expand the data set to see if including different environments, we are able to reproduce better these results. Also, the dimension of the box sizes, yes, it could be. I don't have an answer because at the moment we are using models containing 200 atoms to generate the data set because it's expensive, as you can imagine. I don't know if we could use 1,000 of atoms in the DFT calculation if we would be able to reproduce better the medium range. Is something that should be explored. Another point is the inclusion of long-range interactions. It has been shown, I read a paper on silica glass a few days ago, in which they show that long-range interactions, so if you include long-range interactions, you improve the description of the first sharp diffraction peak in silica glass, but it's not enough. So our model reproduces quite well, even if we are not including long-range interactions. Another problem, but maybe this could be, the main one is the quenching rate. I think that the quenching rate is important. And in the time frame that we can explore, I think that the variation of the properties are not huge. I mean, we should go towards lower and lower quenching rate, because what I see when I do simulations, or when I did, is that the property changes when you have the melt. Once you are below the TG, the computational TG, nothing happens in the simulation. I mean, you see the vibration, but the medium range order is trapped to the melt one. So I think this is the major limitation, but also the other one are important to investigate. Yeah. There is a lot of work to do.
All right, they beat you on the hand raising. You have time for one more question. Don't forget, you'll be eating into your coffee time, which is next. But also, I'm sure Alfonso would be glad to talk to you personally about another question.
Yeah, for sure.
Next one. So this is Martin Letz from SCHOTT. You showed an impressive agreement between your machine learning potential and the DFT calculation on the vibrational density of state. So taking this into account, later you showed that there is still a discrepancy in the thermal expansion. I would expect if you get such good accuracy in the vibrational density of state, because it guarantees all the low temperature thermodynamics of my system, I would also expect that the thermal expansion should be correct. Can you explain?
Yeah, actually what we see is that the vibrational density of state strongly depends on the local environment, mainly. So, whereas the CTA, I think it depends also on the free volume that you have in your system. And in the simulation that I have shown, the machine learning potential that we use in that case didn't include the dispersion correction, which leads to an underestimation of the density. So I don't have the results because I haven't tried it, but maybe if we include the dispersion interaction, we would have a better agreement. I mean, it's not working. A better agreement, more similar to the CTE, so to the experimental data. Okay, we can discuss.
Okay, it is time for the coffee break. Is that back there? So it's in the back. And don't forget to come back.
Sorry, can we just pause before we
Wait a second.
Apologies. I'd like to invite Professor Monk to the front. We'd like to start handing out some presents before you get going. For the best question on Monday, we have Carolini. Come on down and pick your present. We have some nice mugs, t-shirts, and tools. And go ahead, there's shirts, there's mugs. You can choose whatever you like. And for yesterday, Rachel, who continues to ask good questions. If somebody could take a photo with us all after we got the presents, that'd be great. And then you can have your coffee. Keep asking questions. We got t-shirts, we got mugs. There's also multi-tools.
What? Whoa, that's so cool. Everything's so cool.
Take your pick.
Oh, is it like, how to say in English? To measure?
Tape measure,
Yeah.
there's a level, there's some tools.
Oh, and some tools.
All right. Wonderful. There was a technical difficulty. So the next speaker is Marcos de Oliveira, and he's going to be talking about hybrid glasses, not what's in your program.
Thank you very much. So I'm an NMR specialist since always, and then I usually speak about NMR on this class. So this is the first time we decided to change a little bit topic, so we'll speak a little bit about hybrid glasses. So just so you don't leave with the impression that this is an oxide glass school, because it's a glass school, all types of glasses. So I speak a little bit about different type of glass. And before that, I will just show my background. I don't know if you have a pointer here. Yeah. So this slide here represents more or less my entire scientific life. So here it's NMR. Of course, should be a bigger circle here, but. And then I have worked before with hybrid materials, working with NMR for structural characterization of these materials. And part of my life I have worked with glassy materials, or the standard glasses we are used to, the oxide glasses. Also studying them by NMR. And nowadays I'm working this intersection here, so I'm doing NMR on hybrid glasses. So this is the review of my activities. So this is our laboratory. So this year we won't have the chance to visit the laboratories here because of logistics. So we have these 4 spectrometers available nowadays, and we can run different magnetic fields that goes from 240 megahertz to 600 megahertz. And this allows us to investigate a large variety of systems. Henrik showed the periodic table in his talk, and we can explore most of those elements that are characterized as difficult or unpractical. And before speaking about the hybrid glasses, I will speak about a class of materials that where the hybrid glasses derive from. That's the metal-organic framework materials. So I will speak about metal-organic framework, but we have also other types of metal-organic compounds, and many of them are glass formers. So I will show some examples today. So a metal-organic framework, for those who are not familiar, is a system where we have metallic nodes, can be a single metal or a metal cluster, and the organic linkers. Usually these organic linkers where you have more than one active group here, more than one functional group. And then we put them together and form this structure here that we can call a framework. They can be 3-dimensional, 2-dimensional, single-dimensional. So when it's single-dimensional, we don't call metal-organic framework because we don't have the framework anymore, but this is another story. So the interesting properties of these materials is how this structure is organized, and we have porosity, and you can have very interesting properties. So they have really large surface areas, so it can go to 2,000 square meters per gram. We have the possibility to functionalize the surface here, and we can tune the pore structure here by changing metallic centers and organic linkers, and we can have an infinity of possibilities. So we can do whatever we can, what our chemistry allows. Né? So for these interesting properties that these materials have, we had the Nobel Prize last year for the guys who developed the materials for the first time. Just to show how relevant the topic is. So because of the porosity, we can use them for this variety of applications. I just put some here. So for gas storage, so I forgot Portuguese here, but maybe I think you can get from the pictures. So for gas storage, for gas separation, so some molecules will go through this porous network, others will get trapped, so you can separate gases. For chemical sensing, when you functionalize the spores with some active species. For catalysis, heterogeneous catalysis, photonics, so and you can have luminescent MOFs, semiconductors, and so on. So the applications are up to your imagination. And a specific class of these metal-organic frameworks are the zeolitic imidazole frameworks. They are the first one where people saw the formation of classes. And the zeolitic imidazole frameworks are based on single metal centers connected by these organic linkers, that where the name comes from, some imidazole type linkers. So you can have different R groups here, but all of them has this imidazole structure, the central imidazole structure here. And the metals are interconnected by this species here, by this organic linker, as it happens for zeolites when we have silicon-oxygen-silicon connectivities. So you can imagine now that you can make a parallel between this system here and a silicon oxide. So if silicon oxide forms a glass, why not this couldn't form? So it's a similar topology. So then it was in 2014, 2015, they realized for the first time that this the ZIF classes, the ZIF materials, they have a liquid phase. And of course, if they have a liquid phase, they started to explore this liquid phase. And when we quench them from this liquid phase, you can form a glass material. There are also other strategies. You can, for example, do mechanical amorphization of these materials. You also get a formation of classes. The problem is that you cannot form glass with any MOF. It has to, because they undergo decomposition, these organic linkers that can decompose at certain temperatures. So depending on the system you have, maybe you cannot reach the liquid phase, and then you cannot form the glass because the sample will decompose before forming a glass. So not all MOFs will form a glass, but many of them can form glasses, and people are exploring to see how far we can go with these glasses. So this is an example showing the glass forming ability of this guy. So here it's the ZIF62. It's the most studied MOF glass. The ZIF62 has two different organic linkers, the pure imidazole and imidazole with a benzene ring. I will show in details in some slides. It has a really high glass forming ability, higher than some known glasses. So, and also a very high viscosity in the melt state. And then after discovery of these glasses, so people characterize them as the fourth, it's missing a TH here. It's the fourth class of man-made glasses. So who characterized it like this was Yue, that was in the ICG conference. So we have the oxide glasses, metallic glasses, we have organic glasses, and now, since 2014, we have also these hybrid glasses here. So I put the ChatGPT logo here because I just asked him to create this slide, and I'm just using as it was created from there. So if your figure is here, it's not my fault. Maybe he took from somewhere and put here. Yeah, we never know. Maybe he took a figure that couldn't be here. Then I'll speak a little bit about the applications. So the crystalline MOF is porous, and when we go to the glass phase, sometimes they keep the porosity, sometimes not, depends on the system. But for example, for the ZIF62 glass, that's I should put the molecules here because we are so familiar with this MOF that we forget. So this is the one I was speaking. It has imidazole linkers and benzyl imidazole linkers. Benzyl imidazole is imidazole with a benzene ring connected. And when you take the crystal, it's all very well organized. And we are showing here an example of methane, if I'm not mistaken. No, it's C2 ethane. Whatever. It's 2 carbons and 6 protons. And all of them can go through the crystalline porous network. When you form the glass, then we have here the intake of the gas in the MOF structure. So this is how much gas is getting trapped inside the MOF structure. So you see that for CO2, we have this uptake here, and then it stabilizes. And for the ethane here, it's much slower, and then it reaches to the same point here, there. So this is they took the glass, the crystalline MOF, melted it, quenched it, and we have the normal glass, MOF glass, and then it has some selectivity, but not that much. And then they made in a different process. They just pressed the melt, like we do with oxide glasses. And then they can reduce this pore size distribution here. And now it's much more selective, so only CO2 will go through. The ethane you get retained. So this is a very new paper. It's from 2024, if I'm not mistaken. There are some people here from Jena. It was a group in Jena from Alexander Knebel who developed this work. This is another work from the same group, because usually when you see pictures of these glasses, I should have put more here, but they are always like this. They are really small, full of bubbles, cracks very easily. So this piece here has 1 millimeter. It's a big piece for us. So it's really hard to make big glasses with these guys. So they are good for fundamental science, but for real applications, we are still far from using them. So this is a work also from Alexander Knebel, where they could make a big membrane. By big, I mean this size. But of course, if you can make this size, you can do like they were doing in Middle Ages. They couldn't make a big glass window, but they could make small glass pieces. And they put the glass pieces together, and they could make a big window with these pieces of glasses. So this is more or less the idea. So you can have a window that lets some gases go through and block other types of glasses. So you have an active window that you could use, for example, to filter pollution or whatever. So this is the strategy they used. So they were able to make a small membrane, and then they encapsulated this membrane between two. It was a kind of holder, and then they could fix this membrane here and make a solid piece of material. So besides the ZIF glasses, we have other types of MOF glasses. So these are, for example, glasses made with carboxylate species. So we have this species that has this double oxygen in the active group here. So it's a C double oxygen, single oxygen. So they can connect, for example, in this case, zircon clusters and form a metal organic framework structure. This framework structure, just by itself, it decomposes when we heat it up. And they found a strategy to anchor these organic groups here, plus these acidic sites, to prevent the decomposition. So it was holding the structure together. And then they could melt it and form glasses. So this is the pieces of glasses that... Here, these are good examples of MOF glasses. It's always things like this, like this, like this. It's not... It's never pretty. Like, it's always ugly pieces of glasses. And here's another example. So you have also with these aliphatic groups connected by magnesium clusters, they can also form glasses. The advantage of these types of clusters here is that there are more possibilities for connecting with different metal nodes than in the case of ZIFs, where you are more or less restricted to these 2+ transition metal ions. Here it's an example of a compound that it's not a MOF, it's a coordination polymer. And it's also made with imidazole, and it has also phosphorus groups. So we have, it's hard to see here, but we have phosphate groups connecting this tetrahedra with cadmium. and the imidazole making chains here, so it's a linear molecule. This can also form a glass under now mechanical amorphization, and they have seen that the glass material has stronger or higher conductivity than the crystalline counterpart. So they explain it by the absence of grain boundaries in the glass that we would find in the crystalline materials. And going a little bit ago now in parallels between this MOF glass science and what we were doing over decades in the oxide glass science. So this group from Sebastian Henke, they decided to do the modification of these MOF glasses by adding cations there, by adding sodium. So they are formed by zinc, that's 2+ species. So they added sodium, that's 1+. So the idea was to modify the network. And they could do this, so they could add the sodium species there. This is what they were planning to do. So the idea is to put these sodium guys here, and they would create non-bridging imidazole groups, and the sodium would compensate this. They measured the TG. The TG is sensitive to the amount of sodium you put in the structure, so the sodium is doing something to the network. And then they did some DFT calculations and NMR experiments to see what kind of coordination they have in these classes. So what they see here, it's a mess. You need to read the whole paper to understand what's happening, but they have a big supercell, and they calculate with DFT all sodium NMR parameters for all sodium atoms. Then they take only those sodiums that are in these different units here. So we have units with imidazole, 1 sodium and 1 zinc, only 1 sodium or 2 sodium ions here. And then you make subspectra of these subsystems. So you see that when you have 4 coordinated sodium, you have something like this. When you have 3 coordinated sodium, you have something like this, and so on. And then when they compare with the experimental data, they try to see, it's really hard I would say it's not definitive, but this is what they did. So they just compared the region, the spectral region we have experimentally, with this kind of species that would overlap with our experimental region. So although you have no close agreement here, we can see that for these nodes with 2 sodium and 1 sodium, they are the ones that have the higher overlap with experimental data. And then from this, they conclude, of course, they also did PDF analysis. They also have other experiments. I have we call in Portuguese a viés, I don't know, a bias. So I took on the NMR data, but they also have other results. And the idea is not, you see that sodium is not a typical network modifier. It's connecting imidazole groups, so it's a network former in this case, as the zinc is also a network former for these systems. So in the end, they call it alkali ion modified zeolitic imidazole frameworks, but actually sodium is actually acting as a formal network former. After discussions with Caipirinha, with Phil and Ben, then I also started to talk about this, but to think about this by Ben's definition. We have here less imidazole available for each network former. So this is why the TG is changing. So this is why sodium can be considered it's modificating this structure. I'll not get into this discussion because it only works with Caipirinha. This is a theoretical work. I put this slide here because people start to ask me, but it's a liquid. How it's this liquid? You imagine, liquid is a liquid. You have things diffusing. And here, in this study, they were trying to investigate more or less how this liquid behaves. Né? So by the molecular dynamics, they see that for lower temperatures, for lower temperatures, have the imidazole units connected to zinc units. And then when you start to heat the sample, you start having fluctuations in distances here. You also have mobility of these imidazole groups. And suddenly you have disconnection of the imidazole groups. They get so far that you don't have a bond anymore. And then these guys can be they disconnected all over the network, and then they can disconnect to one zinc and connect to the other one. And then you have this motion that can be considered as a liquid phase. No? So here it's just a plot showing how the coordination changes when you go up in temperature. Now, you start having other coordinations like 3, 2, close to 1, meaning that these species are being disattached from the zinc species. And from now on, I'll just show a little bit what we are doing. So for this, we need to understand what people are doing to characterize these guys. So I took this figure here from this review. They put more or less all techniques that are being used to characterize these guys. And we have here, for crystalline materials, it's mostly a single crystal XRD, or also X-ray scattering, and so on. For the transition, we have the DSC analysis, the DMA. NMR also can study this transition from crystal to glass. You can study, for example, this example here is a deuterium NMR as a function of temperature. You can see this motion happening. Molecular dynamic simulations. And for the glass structure, it's usually diffraction techniques, the total scattering of X-ray on neutrons, mass NMR, EXAFS, and so on. This is what people are doing to characterize this species. From NMR, I can highlight this work here from Madsen and Sen Sabiasashi. They have measured by solid-state NMR at high field the zinc 67 spectrum of these ZIF glasses. So you see this narrow peak here is the ZIF crystal. And when we go to the glass, we have this broad distribution. This is because we have a distribution of electric field gradients around the zinc ion. And so they can see that we have a strong disorder in the zinc coordination. Before that, people were just doing carbon NMR. So from carbon NMR, you just see that you have the organic molecule. Before, in the crystal, it has one structure. And when you go to the glass, it's the same organic molecule. The carbon NMR doesn't change. And they also see some change in the nitrogen NMR, some broadening, meaning that the disorder in these materials is in this connectivity between the cadmium, the zinc, and the imidazole linkers. It's in the metallic center, the disorder. So this is more or less what we have been doing. Zinc is a hard nucleus. It's challenging. So we had decided to replace zinc by cadmium to do a fundamental study of how this disorder happens. So this is the first attempt that Renato did. Renato has a poster downstairs, Renato? So he took a sample pure zinc compound, for example, the ZIF4 in this case, and he started adding cadmium. And we see that we have a structure here, and suddenly we have another structure. They don't mix together. So he had a mixture of pure zinc and pure cadmium compounds. He couldn't put zinc and cadmium in the same structure. So we moved on. So if we cannot put both together, let's put only cadmium. Samples solely with cadmium and imidazole, they didn't form a glass. At least in our case, not. But in the literature, it was reported after formation of glasses from pure imidazole ligands here. But they have some strategies of amorphization before melting. But when we add another organic linker here, you see this is the crystalline material, the S-synthesized material. So it's pretty crystalline when you have no benzylimidazole in the structure. And when we add benzylimidazole, the second linker, then we disturb the structure and we cannot find the crystalline configuration. and then we lose crystallinity. But even though we were not interested in having crystals, so we just wanted to explore glass formation. So even though we lose this crystallinity, it doesn't matter because we are going to melt the sample in the end. So this is a study to see more or less what this benzimidazole is doing with the structure. So we could measure by NMR the porosity of these materials. Who measured this was Professor Eduardo. So he did time domain NMR, and in time domain NMR they can measure the melting of liquids. And from the melting of, in this case it was, I forget now, it's hexene, I think, I don't remember now. But it has a dependence of the melting temperature with the pore, with the volume of the pores where it's confined. So from this confinement, from this changing the melting temperature, they could find distributions of pore sizes in these materials. So here we see all these curves together. So for the crystalline materials, we have a little bit larger pore distribution, while for the materials with benzimidazole, we have narrower distributions of pore sizes. I think it's 10 minutes now. Né? So this is our first attempt to make glasses from these guys. So we don't know if the guy forms a glass, so we need to test. So what we do, we put inside the DSC, the crystalline material, and then we do a DSC run until we see the melting. And then we cool it down and go up again to see if it formed a glass or not. So this was one of the first tests. We heat it up, we have the melting, and then when we cool down, we have a crystallization of the material. And for these 3D materials, it's one of the only examples we have that shows recrystallization from the melt. So this was a surprise. We would not expect it to recrystallize. If you do this, for example, with ZIF62, you can cool it down in the inertia of the oven that it's going to become a glass. But here we have this recrystallization. And when we do the second upscan, you see it's crystalline again. We just have the melting here. And then we just did a fast quenching of from the melt. And then we could obtain the glass, so we can see a glass transition, the recrystallization peak, and the melting again. So this is how the glasses looks like. This was not the first ones that Renato did. The first ones were much worse. But after some trial and error, he could get these really nice pieces of glass. And here it's just showing that it gets completely amorphous after forming the glass, as we would expect. Né? So we have studied a little bit this recrystallization, and we saw that when you start from the glass, you have recrystallization, and then if you start from the recrystallized material and melt it again, when you go back to the glass, you don't see the recrystallization peak anymore. So it's not a reversible process. Something is happening with the structure. We have decomposition, and we cannot crystallize and melt the sample forever. Né? Partially, the sample is getting decomposed, and this can be seen by this EPR signal. So when we do EPR before the melt, we have no signal. After the melt, we have the signal in G equal 2. That means we have defects in the structure. I'll skip this one because I have no time to. This is just for this cadmium system. We can see that for the carbon NMR, we have similar spectra here, meaning that the organic linkers are there. This happens for all MOF classes. But when we look to the nitrogen and to the cadmium NMR spectrum, we see that we lose resolution here. So meaning that we had the disorder, like happened in the zinc system, the disorder is concentrated in these metallic domains. So just to finish, usually people characterize the samples by PDF analysis, and they can see how the very short coordination is arranged in these samples. So this is a work from Sebastian Henke with the same system with cadmium, and we can see the short range ordering here. But then we did NMR and we saw disorder. So we said, can NMR tell us also how the average environment is, because this is more or less what X-ray is seeing. It is the average of the local environment. So we did this NMR experiment that I had about 30 slides. I said, no, I have 1 hour. So then I put a lot of things here. Henrik already explained this. So we have an experiment to measure dipolar couplings. So I have 2 experiments. When we are doing the experiments rotating the sample, so we have 2 dipoles here, phosphorus and boron. If we rotate them one around each other, the dipolar coupling between them will go like this. So in average, the dipolar coupling is 0. This is why we spin the sample. But then if we invert this pulse here, this guy here, in the middle of the spinning period, then we get this behavior here, and we can refocus this dipolar coupling interaction. So by comparing this signal with this signal, we can know the intensity of the dipolar coupling interaction. So I just skip this one here and fix to what is important here. So this is a spectrum showing the difference of those 2 signals as a function of evolution time. So if the difference is large, it's because the dipolar coupling is large. If the difference is small, it's because the dipolar coupling is small. But the idea here is just to compare the crystal, that's this blue one here, with the glasses we obtained. In the beginning of the curve here, we have the same behavior, meaning that the average environment, how much protons each cadmium is seeing around it, for the crystal and for the glass, it's the same thing. So although we have disorder, we don't have big defects like ligands that are missing or some things like this. So probably the disorders concentrated in the variations in bond distance and angles, not in defects in the structure. Although we have some defects. I don't know how much time do I have. I'll just show 2 more systems here. So this is, we are investigating this stuff. Now we try to put other metals in the ZIF structure. So this is our attempt to put gallium in the structure. So it works quite nicely. We are still characterizing this structure of the system containing zinc and gallium. We don't have a final crystallographic model for this. But when we look to the gallium NMR, we see the gallium is hexa-coordinated, while the zinc is tetra-coordinated. So we have 2 coordinations happening in the glass. To know, since we don't have the single crystals and we don't have X-ray diffraction analysis, I have an NMR spectrometer, so I try to learn from NMR first. So we did this experiment where you can detect, it's an experiment where we measure protons, but we take polarization from gallium. So we measure just those protons that are connected to gallium. And when we get the spectrum, that it's this red one here, it's pretty much comparable with the blue one. The blue one is the imidazole proton spectrum. So we see that the gallium is indeed coordinated with the imidazole species. Here we have some other peaks, probably water coordinated with gallium. So probably we have some sites where water is in close proximity. So this is an experiment that's based on spatial proximity. So doesn't mean that things are making bonds, but it's clear that the gallium should be connected with nitrogen. And here we have a nitrogen spectrum that shows 2 different peaks, and then we prove that nitrogen is coordinated either with gallium or with zinc, so we have both coordinations in the sample. And when we try to make a glass of it, it forms a glass. We can see glass transition here. Doesn't get surprised. Glass transition in these materials, it's always like this. It's really... And then we make the glass. Then the part that has zinc forms a glass, and the part that has cadmium, it's still crystalline. So we can form, I don't know if I can call it a glass ceramic, if it should have a thermal history to be called a glass ceramic, but we can chemically control the amount of crystal we have in the glass, because we just make the glass and the rest doesn't become a glass, it's still crystalline. So this is as far as we went with this research. And the last one, Guilherme showed in his fire talk. So we have composites of these MOF glasses. with luminescent MOF species, so it's this linker here connected with europium. And then he sees that after making the composite, we still have luminescence of these guys, so it will be in his poster if you need more detail. But what I would like to show is that NMR can show us, of course, you can take the ZIF glass and the luminescent MOF, put both together, and call it a composite. If you do luminescence, it's luminescent. But do you have only two powders mixed together, or you have really a composite where the MOF is penetrating in the glass structure? So we can see this by NMR. So we see here a carbon spectrum of the luminescent MOF. So we have the organic linker here, and this carboxylic species. And here the imidazole spectra. So in the composite, we see both together. Of course, if it's just two powders together, we would see the same thing. But some things we see, for example, these carboxylic groups, they shift, meaning that something is happening with this luminescent MOF. And when we do a correlation experiment, the carbon-proton correlation, we can see cross peaks that shouldn't be here. So we see carbons of the luminescent MOF coordinated with protons that are here, coordinated with these protons here that are from the imidazole. So we have imidazole protons in proximity that are from the ZIF62 in close proximity to the luminescent organic linkers. So I call it luminescent organic linkers. It's not that the linker is luminescent. The linker is from the luminescent MOF. No? So this proves that they are in close proximity, so the MOF is penetrating the glass structure. So I'd like to thank my students. We have a big group, it's me and Heineke together, and I put here the students that I'm supervising, the ones that are involved in these works with MOF classes. And thank you very much for the attention.
All right, the talk is open for questions. It's a great talk and you have time, so all right, let's start here.
Yeah, thank you, Marcus. Really great talk, giving a perfect overview over MOF glasses. I was wondering about the reversibility of the crystallization. So when you first prepare the crystalline material and then glassify it, you get certain spectroscopic changes. Can you then crystallize it again, and do you get the spectrum back of the crystal, or do you get additional signals that show that there was some disorder in the glasses that...
Actually here, in the first recrystallization, we have a better crystalline material than before. So this is the synthesized X-ray of the material, and the red one is after recrystallization. So somehow it improves the crystallinity. But then when we try it the second time, then it starts to degrade, and then the third time it degrades a little bit more, and then at some point you cannot recrystallize anymore.
Yes, yes. No, this I understand with X-ray, but have you done the NMR on the recrystallized material as well to see if there's other signals there?
Yeah, no, we did, and from the NMR we cannot see the defects. It's always the same spectrum, and then this is why we did the EPR. From EPR we could see this signal in G equal 2 showing up, and probably for NMR these guys are invisible. So this is why we always see the same spectrum there.
Don't forget to identify yourself.
Sure. I'm Rishikesh. I'm Rishikesh. I'm from Glidewell Dental Laboratories. First of all, Marcos, nice talk. I had a question on the glass forming ability and relaxation of these glasses. So as Professor Zanotto and Moros said in their definition, that the ultimate fate of any glass is to turn to a crystal. Can you comment on how long will these glasses take to relax back to a crystal at, say, room temperature?
Yeah, for example, in the ZIF62, it has this porous network structure, and the activation energy to go back to this is huge. Like, so I believe they don't recrystallize. You would need to give much more energy, but then they decompose before recrystallizing. So you need to you destroy this framework here, and it's the energy to reconstruct it. It's really high. So I think this is why they do not crystallize. So in this case of the Cadmium system, we don't have these cages here. It's a dense structure. And then the activation energy is much smaller, so this is why they crystallized.
Also, another question was, what is the typical, say, strength of these glasses? How strong are they? The typical strength of these MOF glasses? Like, what will be the flexural or the strength at which it breaks?
Yeah. No, I don't have this in my mind now. I cannot answer again.
Thank you.
No, I think we have an answer for.
I'm in this row.
Hi, I'm Anna from Jena, Anna Tondorf. And right in the beginning of your talk, you had physics-absorption isotherm type 1. And then later you said you measure porosity with NMR. Like, why do you measure the porosity with NMR instead of physics-absorption? And does the classification for the glasses, for the hybrid glasses, change the classification of the physics-absorption isotherm types?
Yeah, it's really challenging to do this gas adsorption analysis in these samples. We did, and but they always take a long time, and it's always challenging. Sometimes you don't have the curve doesn't go to the end because the liquid nitrogen is over. And then we compared in this study here the NMR with the BT analysis, and we have the same results. So we did the NMR just to have a quicker way of measuring this porosity without needing this long adsorption experiments.
And the BET, do you still use the same basis for calculations, or do the basic assumptions change for the hybrid glass?
No, it's the same assumptions. Yeah.
Okay. Thank you very much.
Hello, thank you for the great talk. I'm Mehmet, coming from Penn State University. My question will be a bit on the fundamental membrane size. So I really wonder how the processing conditions affect the MOF properties for the gas separation, because in the conventional membrane size, like for the polymer-based membranes, there are some pretty reliable methods to control that size, like spin coating or solution evaporation methods. But for the MOF glasses, so there will be a melt quench process. So how that affects the porosity and the gas separation properties. And as a follow-up, also in the membrane size, so there is this selectivity and permeability trade-off. So what's the typical thickness range of the MOF glasses that we can maximize the permeability to keep the same selectivity?
Yeah, I'm not very sure. This work is not mine. It's from a group in Jena. But they have some engineering to make this reproducible. So you see that I showed two different processing of the glass here, and it changes the porosity, it changes the selectivity. So this is something that needs to have a fine control. Other problem is that these guys, they absorb water, and then at some point they stop working. So when you are going to use these materials, you have to use layers of materials. So you have to use other materials, for example, to absorb water, and then let them off absorb the gas. So there are some challenges that people are exploring. So this is still work in the beginning. So I don't have all the answers.
Thank you so much. No worries. Yep.
Thank you for your very good talk. I just have one very quick question. How to introduce European ions in your glass? What kind of raw materials you are using? And also, what's the valence of your European ions, 2+ or 3+ in the glass?
European is 3+ there.
Yeah.
And it's a mixed metal. It's europium and zirconium with this organic linker, this benzene tricarboxylic acid. And the synthesis is done in ethanol, and it's a solvothermal synthesis, that's a standard synthesis. So I don't know what other details. And then we make a normal europium moth. And then this guy, we ball mill together with the ZIF62.
Yeah.
And then melt the ZIF62. This moth has a large temperature, how do you say, stability.
Yeah.
So it's stable until the melting of the moth glass. And then we can melt the glass with the moth alive there. And then it stays pieces of the moth inside the glass. This is the idea.
Okay.
And we ball mill it before to have a very thin grain, so we have a good distribution of the moth in the glass.
Yeah, thank you. I see.
Any others? All right, I have one, but I think people were skirting around the question when they talked about crystallization. How much control do you have on the material? Could you potentially make a glass ceramic, crystallize the glass to almost crystalline?
And this work of Sebastian Henke that I showed here, they tried to study this control of crystallization. It's not very easy to control the crystallization, and you need to deal with this decomposition. So if you do heat treatments for different times, then you are changing the amount of crystals, but you are also decomposing the sample, so it's challenging.
Wonderful. Thank you very much for that.
Thank you.
Okay, we can move on to the next talk. Which will be given by Helmut Eckert, and he's going to talk on the glass structure by electron paramagnetic resonance spectroscopy. Say that 3 times real fast. All right. Thank you.
All right, yeah. First of all, I'd like to thank Edgar and the CERTEF team for organizing this 4th school and doing it one more time. While the CERTEF funding is ending from FAPESPI, it's great that we have this possibility of really finishing up this project that's been running since 2013 under Edgar's leadership. And the last 2 classes I have moved my presentations from NMR to EPR because I now have very competent successors in the IFSC. Markus and Henrik are taking this now to new directions and to a brighter future. And so what I have switched my presentations to are EPR, the topic of EPR, which was actually one of the motivations of me to come to IFSC to begin with. And I want to pay special homage to Claudio Magon, who was the EPR expert at IFSC for many years. And I'd like to thank him very much, dedicate this talk to him, for teaching me EPR and making me learn new things, and also thinking about what can EPR spectroscopy do for glasses. And so you can see here the outline of my talk. First, just a little bit of fundamentals, basic fundamentals, and then there's 2 types of EPR spectroscopy, and San Carlos was pioneering in actually doing with Magon both of them in parallel. namely the classical continuous wave EPR spectroscopy, which I'll introduce first, and then the advanced pulsed techniques that actually provide a lot more information and insights also into glasses. And I will, along the lines, always illustrate this with some examples to glass science topics, so what we see, what we can learn, and what the informational content of EPR is to the structure of glasses. Okay. Okay, just the fundamental principle of EPR. It rests with the unpaired electron spins. Unpaired electron spins, the spin concept initially introduced by by Uhlenbeck to explain a discrepancy that the Schrödinger theory posed with regard to the experimental observation of the hydrogen emission. Basically, Gudsmit and Uhlenbeck concluded that the Schrödinger theory wasn't complete with the 3 quantum numbers, but there was had to be a fourth one, namely one that corresponds to an angular momentum with quantum number 1/2, so there would be 2 additional electronic states. And this concept made the agreement with the experiments complete, but it was sort of initially a phenomenological construct. What do you have to do to make things right? And then to prove the reality of spin was done by the very famous Stern-Gerlach experiment. The Stern-Gerlach experiment proving orientational quantization of angular momentum, and in addition also providing the magnitude of the electron magnetic moment. This was done with the famous experiment in 1940, and Stern received the Nobel Prize for this. Sorry, it was the experiment was done earlier, but in 1942 the Nobel Prize was given on this. Okay, so what are we looking at with EPR spectroscopy? We are looking at the magnetic Zeeman interaction of the electron spin with magnetic field. You can see here the magnetic moment is given by the Bohr magneton multiplied with angular momentum operator, and G is the so-called Landé factor, which is constituted of a spin contribution. If there was only spin, it would be have the value of 2. But since there's always also contributions from orbital angular momentum, it could differ from 2, and the formula you see there describes you the formula you see here describes you how to combine the spin angular momentum and the orbital angular momentum and the total angular momentum to get this value of G. G is one of the observables in EPR spectroscopy. Okay. Yeah, in EPR we are with regard to I will talk more about the G before, but for this moment, just want to tell you that in the solid state, G, which controls the interaction of the magnetic moment with the magnetic field, is an anisotropic quantity, and therefore it is a tensor. So we have to deal with tensorial properties of the interaction. Now I want to talk a little bit about the 2 methods that are being used in EPR spectroscopy. As I mentioned before, the classical method is the so-called continuous wave spectroscopy. And I will actually illustrate this first. We'll get back to the pulsed method later on. So we're talking right now about the classical EPR spectroscopy, which still, I would think, is about 75, 2/3 of all the work published in EPR spectroscopy deals with this method. You can see here how the Zeeman level, the Zeeman interaction is increasing with increasing magnetic field strength. And so you get this splitting, which is proportional to the field. And basically what we're doing is we're applying electromagnetic waves to cause transitions between these two spin orientations, m equals 1/2 and m equals -1/2. Okay, here's the machine, the one that was also used in the work that I will describe later. It's the experimental setup. We are basically observing or recording microwaves that are emitted by a gun diode, and here is the detector. So the machine is exposed to microwaves. Our sample is here in a cavity that is connected to this line over here. And the sample and the cavity, they are in a magnetic field. Yeah? So this provides the magnetic flux density we need for the experiment. And what we're going to do is we're going to change it. We're going to sweep the magnetic field while continuously applying a constant frequency and recording the detector signal. Okay. Okay. When now the field passes through a value where the resonance condition is fulfilled, yeah, so where the electromagnetic energy is equal to the splitting of the energy levels, of the orientational energy levels of the electrons, then the sample will absorb energy, which means it will cause an imbalance in the detector signal. And so we're recording basically a change of the detector signal as a function of magnetic field strength. Yeah? So then basically what you're seeing here, it would be something sort of a Gaussian line, or other line shape, any kind of line shape that might arise as magnetic field is swept through. So before constant signal, then change, and then at larger magnetic field strength, when we're off resonance, again return to the baseline level. Okay. Now, one particular aspect of the continuous wave EPR spectroscopy is the magnetic field modulation, which means what is done is the following. While we are sweeping the field, we are also oscillating it. Yeah? We have changed the field in a sinusoidal function and synchronize this with the detector signal. This has as a result that we're recording actually not the signal itself, but its first derivative with respect to the magnetic field. So rather than observing the signal like this, we see the first derivative like this. This has great advantages with regard to noise reduction, and also it improves the resolution. Basically in the derivative you see more spectroscopic detail that helps you with a line shape fitting. Okay. There are typically about 5 or 6 magnetic field strengths available in EPR spectroscopy. They're typically recording at fixed frequencies, yeah, in the gigahertz range. Typically, 9.5 gigahertz is the most common one. It's called the X band. The magnetic fields are relatively low, so this would be the typical X band configuration. In addition, there's another microwave band that is being used at 35 gigahertz, which corresponds to a Q band, which corresponds to a 4 times larger magnetic field. And then there's the W band at 3.5 Tesla and 95 gigahertz. These are the three most common spectrometers. Only the first two ones here are operating in electromagnets. For higher magnetic field, W band, and there's other ones, D band and so on, you need to use superconducting magnets. Okay, so let me see this. Yeah, I mentioned before that this quantity G, which controls the interaction of the electron magnetic moment with an external magnetic field, is a tensor. So it is orientational dependent, which means that the line shapes will also depend on how the orientation of the magnetic field is with respect to a molecular axis system. Yeah, so the G tensor is basically fixed by the orbitals in which there's a special bonding situation in which the EPR probe is finding itself. And in a powdered sample, the molecular axis system has a statistical distribution with respect to the magnetic field. Yeah? A typical line shape that you would get in this situation is a line shape like this. You see a large, largely asymmetric curve here. This has to do with the fact that the orientational statistics control this line shape, the intensity. Basically, the probability that Z and B are directly aligned is much lower than the B field being perpendicular. Yeah? If you have the alignment like this, then you have this probability. But for the perpendicular orientation, you have all these other probabilities. Yeah? So therefore, the perpendicular orientation is more intense, gives a more intense signal. Yeah? This is a special situation, which is a little bit a simplified one, in which case the tensor has the so-called axial symmetry. Axial symmetry means that you have a main axis, a principal axis, along which you record one component, namely G parallel, and then perpendicular to it you have the other ones. But the x and y directions, so the z direction normally is the parallel axis, and the x and y for the axial symmetric situation are equivalent. You always have this sort of axial or cylindrical symmetry when you have rotational axis with a that is more than twofold, like a threefold or a fourfold or sixfold rotational axis always gives you the same values of G, X, and Gy, yeah, and different from Gz. Okay? And many of the EPR spectra are analyzed in terms of this more simplified model. Even sometimes this is not the case. If you, for instance, have rhombic symmetry, then X and Y have different values in the G components. And then the line shapes look a little different. That's shown over here. So here's just the case of the axial symmetry of the G tensor. And if you have a rhombic symmetry, then you your line shape looks like this, and you can then read off also here Gx, Gy, and Gz. Again, I need to remind you that in the continuous wave EPR spectroscopy, because of the magnetic field modulation, we are recording line shapes like this. These are the first derivatives. So a typical axial signal will give you this line shape. A typical rhombic situation will give you this kind of signal. So basically have then here in this case 2 components of G, in this case 3 components of G that you can obtain by simulations. Okay, so this is one observable, and we can look at it at the G tensor in analogy to NMR spectroscopy, something like a chemical shift. In NMR, we always, people may be more familiar with NMR. In NMR, the chemical shift is the observable that we get from that technique, simply because the chemical shift is kind of the magnetic shielding that is mediating the interaction between the spins and the magnetic field. So in EPR, the G is chemical shift, but its interpretation is a little bit more complicated than in NMR and almost always requires simulations. Okay. Okay, so this is only one observable. The other observable we have in NMR spectroscopy is a magnetic hyperfine interaction. This is basically an interaction between the electron spin, S, and the nuclear spin, I, that influences the EPR spectra if there is interaction and a spin density at the nuclear, at the sites of the nuclei. Then the paramagnetic electron that we are measuring will also sense the magnetic nuclei. And A, the hyperfine coupling constant, is basically, gives us an idea of the magnitude of that interaction strength. Okay. Okay. So in EPR, of course, we are observing both. We are observing the Zeeman interaction with its chemical shift and nuclear magnetic hyperfine coupling. What is the reason for this nuclear hyperfine coupling? It's like this. We have our unpaired electron spin, let's say, in this orbital here. Yeah? Because of Hund's rule, this unpaired electron polarizes covalent bonds that link to nuclei, yeah? Shown over here. And because of the Hund's rule, the configuration of the spin, the sigma bonding electrons over here are a little bit polarized, such that there's a little bit of a higher spin density parallel than antiparallel. Yeah? So that means that near the nuclei here, there is a slight preference of antiparallel orientation. And this basically antiparallel oriented spin density. And now this antiparallel oriented spin density finds itself in 2 situations. The nuclear spins could be in the +1/2 state, or it could be in the -1/2 state. Yeah? So both of them are possible, and both of them will occur actually with almost equal probability. Yeah? But this one, with the antiparallelly oriented spin density and the magnetic orientational quantum orientation of the nuclei, is a little bit energetically lower, more favorable than this one. Yeah? But both of them will occur and you will not really detect a difference. But what's important is the 2 energies are different. Yeah? And so instead of seeing one line in a regular EPR spectrum, you're only seeing 2 lines. Yeah? You see a doublet if there is an interaction of the unpaired electron with one nucleus of spin 1/2, so it is a typical 2-spin model. And then in the EPR spectrum, which is now governed by both interactions, you see each one of these energy levels is doubled. And because we are recording the an EPR spectrum always at a constant energy, we have now in the experiment, we have now the size of this energy arrow here equal, and we get a resonance at two different positions of the magnetic field. Yeah? So we get a splitting into two peaks, here and here, yeah? Corresponding to this situation and that situation. Yeah? Yeah? And this is because also of transition selection rules that the nuclear spin, because we're not doing NMR, we're doing EPR, the nuclear spin orientation quantum number does not change, and the one of the electron changes by 1 unit. These are the selection rules for magnetic resonance. No? Okay, so this is the simplest situation, and if we have an interaction with 2 spins or 3 spins, we also need to give then the spin quantum number of the nuclei, you can calculate the number of peaks that you can expect by this formula here, 2Ni times I is the nuclear spin quantum number plus 1. Okay, for each interaction, you have to multiply them with each other. So this is the general formula from which you can always compute the number of peaks you would expect. Yeah. Now I wish things were as simple as I try to present it here, but there are actually some additional complications that we at some point can ignore, but at some point we need to at least keep them in mind. One simplification I already presented. We are assuming an axially symmetric G tensor, and we can also assume an axially symmetric hyperfine interaction tensor. Yeah, I need to mention that this nuclear electron spin hyperfine interaction is also quantity depending on the direction in the molecule. That is also anisotropic. So it's also to be described by a tensor. So we have, aside from gxx, gyy, and gzz, we have 3 more parameters now for the hyperfine interaction tensor element axx, ayy, azz. Yeah. And not only that, the two, particularly in the case of rhombic symmetry, the 2 principal axis systems not necessarily coincident. So there's 3 more parameters that needs to be specified, namely how the 2 principal axis systems are oriented here relatively. So here, this is the G tensor, the green one here, and this is the hyperfine interaction tensor. Yeah, so there are 3 Euler angles relating them. Yeah. So in the end, there's also a line broadening parameter. You have a 10 parameter fit to a spectrum. Yeah? And here, to advertise a very powerful program to do this fitting is the Easy Spin freeware that we need to give credit to Stoll and Schweiger, who put this on as freeware to do this kind of peak fitting. Okay, but many times, again, this is the most general case. Yeah, many times we are quite confident that we can do the assumption of axial symmetry, and in this case, when there's axial symmetry, then the 2 tensors are coincident because they are constrained by the molecular symmetry. And then things are much easier. Yeah? Because then you only have G parallel, G perpendicular, A parallel, A perpendicular, and the angles are 0. Yeah? And many times you can get along by using this assumption. If you cannot get along, there are other things you can do. You can record at different magnetic field strengths. And you can see here from simulations, this is just a digression here for a nitroxide radical, where these tensors are not coincident. And then you basically record the spectra at different magnetic field strengths. The spectra are different then, because the G values, the Zeeman interaction is field dependent, but the hyperfine interaction is not field dependent. So by working at different fields, you can sort out these interactions. Other things you can do to sort out are pulsed excitation and DFT calculations. You can actually, if you have a well-defined system, you can use density functional theory to compute what these tensors are and how they're oriented with respect to each other. Okay, so let's talk about some practical applications, spectroscopic applications. And one topic that we've been interested in the last few years was the role of transition metal ions in glasses. Yeah? Same thing, rare earths. Transition metal ions and rare earths are potentially EPR candidates. We have to consider that these are not typically spin 1/2 systems, but they have other spin quantum numbers. There could be zero field splittings, but this, fortunately, we can often ignore, particularly in glasses, because the intra-atomic interelectronic interactions and ligand field effects limit us to seeing only one of these transitions in which we are looking at the central 1/2 to -1/2 transition, and then you don't have to worry about the zero field splitting unless you're doing work on single crystals. Yeah, I talked already about the magnetic hyperfine couplings. Because the electrons in transition metal ions have significant contributions from orbital angular momentum, this actually introduces large G anisotropies. If the spin-orbit coupling wasn't there, if it didn't exist, if it was only spin, so there would not be a relationship to orbitals, then there would not be an anisotropy. So the fact that we are observing G anisotropy is a manifestation of orbital contribution to the electron magnetic moment. So basically what we see then is in transition metal ions and also in rare earths, we generally expect broad and sometimes structured line shapes, and the parameters would have to be extracted from simulations. Okay. One important part is not every paramagnetic ion gives an easily recorded EPR spectrum. There's the important Kramers rule here that EPR is generally only feasible if the electron spin is a semi-integral number, so half integer. So this applies to titanium 3+, there's only one electron there, vanadium 4+ as well. We have chromium 3+, which has 3 unpaired electrons and gives a spin of 3½ for this reason. Can give also EPR signal. Manganese 2+, and iron 3+, they are spin 5½ Yeah. Cobalt 2+, spin 3½ and copper 2+, is spin 1½ Again, there's only one unpaired, actually one missing paired electron. I will talk a little bit about copper here because that's an important glass ingredient for biological applications. In the rare earths, you see the same thing. Cerium, neodymium, europium 2+, gadolinium 3+, dysprosium, erbium, and ytterbium 3+ are observable. The other ones generally no. Yeah? The ones highlighted in green are the ones that are most easily measured, namely at room temperature. Because of the relaxation characteristics, These ones in greens are easily observable. They correspond to spin 1/2 systems, and or they, basically to be more precise, they correspond to A states, so they relax more slowly and can be observed room temperature. For the other ones, you have to go to very deep temperatures, typically to helium temperatures, to make these other signals observable. But then if you have a cryostat, then that's easily possible. Okay, so talking about copper. This is the simplest EPR spectrum you will be able to observe for copper 2+ in solids or in a solid, in a very well-ordered solid. What you see here is axially symmetric G tensor and axially symmetric hyperfine interaction tensor. You can see here at the center of this centroid of this quartet here is the value of G ZZ, and here is the value of, so this is G parallel, and this is GXX, which is equal to GYY, which is G perpendicular here. This would be, it would be one peak if the hyperfine interaction was 0. But because the hyperfine interaction is also there, you see now with copper you have a spin 3½ nucleus. You see 4 lines according to that formula that I gave you. You expect 4 lines with equal intensity. And from the splitting between these 4 peaks, you can get the hyperfine coupling constant, so from the simulation of the spectrum. This is a very simple situation, because what we have is the parallel A value, tensor value, has a relatively large number, is 114 Gauss, whereas the perpendicular hyperfine interaction parameter is very small and not resolved in this line shape over here. Yeah. So this is the most basic thing you can observe. And what would happen if things were more complicated? You can see here, rather than seeing this, yeah, the second one on top, on the bottom, there was no hyperfine interaction. Here you see with a hyperfine interaction. What you can see is things look more complicated if the 2 principal axis systems are not coincident, and you see here different orientations. So when you observe a spectrum like this, it could be because of the tensor orientation, but in principle you could also imagine that you could get line shape, could get more complications in this part of the line shape when you have more than one site and that are superimposed. Then you get a superposition of 2 spectra of this type. How to sort this out? You actually need to record spectra at 2 different fields. So again, back to this. This coincident situation with coincident tensors that we have shown before. What does it tell us about the local structure? Well, because the G is anisotropic, it actually shows up like this in the spectrum because of the Jahn-Teller effect. And the Jahn-Teller effect, which is of course a common situation for copper, you actually have a distortion of the octahedron. If the environment was perfectly octahedral, you would not see a G anisotropy. You have a spherical, a cubic local environment. But because of this Jahn-Teller distortion, you get a splitting here between the z square and the x square minus y square electron, the B1G ground state, and You will also get here in the d orbitals that are lower, also get some loss of degeneracy. Yeah, this would be this typical, the classical situation for a perfect octahedron. But with copper, the Jahn-Teller effect always causes, in many cases, a distortion, as an elongation of that octahedron. And that produces the G anisotropy. And that's basically what we see in pretty much everything that we see in the glasses or in crystalline systems as well. Here we see something on dental ceramics. These are still crystalline materials. We have here hydroxyapatite. We see here the splitting. And OCP, octacalcium phosphate, completely, crystallographically related to hydroxyapatite, but completely different EPR line shape. So the local environment of copper substituted on the calcium side of these dental ceramics show the different ways of distortion. But we're not yet there on glasses. Well, actually, if you review the literature on EPR spectra of glasses, you come up with about 2,000 papers, and most of them are not really worth very much more than the paper they're printed on, because they were done in a very uncontrolled way, and reviewing of EPR is right now a little bit, peer review on EPR spectroscopy is a little bit difficult because many times the EPR is just part of a published paper that focuses on something else. So it's normally not EPR experts who get to review it unless you really send a paper to the Journal of Magnetic Resonance or something that's really specializing in magnetic resonance. So then you get these kinds of very different kind of line shapes, and they're looking there and nobody knows what it means. One thing we have to be sure in EPR spectroscopy, the spectra that you will be able to see are very much dependent on concentration. Yeah? So it's important that your copper species you're observing are truly isolated, yeah? That they are not in close proximity to each other, not clustered or anything, because in that case you see line shapes like this. They get spin exchange, you get strong dipolar broadening. So these spectra don't tell you much about. The only thing they tell you is that the material is probably inhomogeneously distributed in the glass. So what it's important is one needs to make sure that you have isolated species by measuring a whole series of samples in which you carefully vary the concentration of your magnetic probe. And here is an example here. This is a very low concentration of copper, 0.5 mole% in this particular glass system. There's a copper phosphate lead oxide glass. So there are studies like this in the literature. Here is one of Rao. This is a good one. You can see here what they did. They really changed the concentration and made sure that up to between 0.1 and 0.6 mole% in this glass system, the spectra are not altered by spin-spin interactions. Yeah? And then they can do analyze these spectra and do some line shape simulations. I'll skip this one, but we're going to the next one. Here, these are some these are now glasses, bioglasses. And you can see here what's also important, and that was something that Claudio Magon always does when he records spectra of glasses. you need to record a baseline also. Basically, you need to record a spectrum in which the dopant is missing. Yeah? And so you need to do subtraction, and then what your result is actually the difference spectrum over here. Yeah? So that is important because, of course, anything else might show up. Something is showing up here, for instance. Anything that is an impurity from another source is showing up. It doesn't show you that this is a copper signal. It just shows you there's an EPR signal there. It could come from any kind of species. So then what we're seeing here is something very interesting. We do recognize that it's hard to see, but we recognize there's still these 4 peaks here from the magnetic hyperfine coupling. We also recognize that the spectrum on this side, on the G parallel side, looks more complicated. To find out what is actually causing the problems here, it's important to simulate spectra. If, and this is now concerns the thing that, of course, in glasses we are most interested in. In glasses, we do not have a fixed local environment like in a crystal, which is a well-defined site, and only a simple one component contribution. But we're having a distribution of environments, and that will cause a distribution of G and A parameters. Yeah? So in the easy spin software, this is called a strain parameter. So from analyzing EPR spectra, we can get values of the strain parameters for G and for A. And what you see here on top, if you look carefully, you see that this is not, they're not equally wide. Yeah? Now this actually is still for a simulation for one particular set of parameters without any strain. The reason these outer lines are broader than the inner lines has to do with the fact that copper has 2 different isotopes, copper 65 and copper 63. And they have slightly different magnetic moments. And because of these slightly different magnetic moments, they have slightly different splittings. And what you're seeing here reflects the natural abundance and the fact that these outer lines are the ones associated with the +3½ and the -3½ spin states of the nuclei. The difference is bigger than this. So this is the normal manifestation of a copper spectrum for a single site. Now, if you now introduce a strain on only the hyperfine interaction, that means you make the difference bigger, and then the line shape would look like this. If, on the other hand, you ignore any strain in the A parameter, but only consider the strain, the distribution of the Zeeman energies, then the line shapes would give an equal broadening of all of them. Yeah? What we observe in the EPR spectroscopy of glasses in general is this situation down here. Yeah? And this is the situation where the G and the A strains are correlated. That is, so rather than having fixed G value, we have a range of G values, but the range of the part of that distribution that has a larger G value has a smaller A value, and so on. So G and A are interdependent on the local structure, and you basically, for this reason, our EPR spectra always look like this in glasses. This would be interesting to actually verify by DFT calculations. I'm not aware that has been done. If there was a positive correlation, it would just look the other way. Yeah? But this is the normal one. Yeah. So what can we learn from the parameters? So if we extract from the spectra, we can get the G parallel, we can get the G parallel value relates to some bonding parameters. It's basically the energy of the B1G to B2G transition that you can extract experimentally from UV-Vis spectroscopy. Lambda is a spin-orbit coupling for free copper 2+. That is a fixed value. The same here, this parameter P. And what the chemical bonding information that is in the value of G parallel and also G perpendicular lies with these parameters that define the covalency of the in-plane sigma bonding and the covalency of the in-plane pi bonding. And then this formula allows you to basically get here the alpha square, and once you have the alpha square, you can also get the beta square. Nowadays, you would not probably work like this anymore. This was before the DFT arrived, and now actually you could probably calculate directly from DFT all these parameters. Here's an interesting plot that Bogolomova did some years ago for the EPR spectra of copper in different kinds of glasses. Yeah? Different kinds of glass systems. You can see here this anti-correlation between G parallel and A parallel. Yeah? Large G parallel means small A parallel, and large and small G parallel means large large A parallel values for different glass systems. You can see how the glass matrix influences the bonding parameters of G and A parallel. Yeah, this is just to quickly give an overview of the periodic table, what elements are feasible. The ones in green, we already showed you, those are the ones that you can easily or record at room temperature. The ones in blue are also possible. And I've also marked here the ones in yellow, because you get data about these elements, even if they do not form paramagnetic species, but rather using electron nuclear interactions observed by pulsed EPR spectroscopy. Okay, so just some important messages for standard EPR on glasses. Low dopant levels are important. You need to measure concentration dependence. If you don't see a signal, it doesn't mean the species isn't there. You need to change temperature to make sure that it really isn't there. It is not invisible by relaxation problems. You can actually use this for quantifications with a known standard of EPR signal intensity. You need to do easy spin simulations, and yeah, relate to structure. Today you would compare the spectra with structural scenarios that you come up from molecular dynamics simulation in connection with DFT. Yeah? And then compare your experimental data with those scenarios that you come up with a computational approach. Okay, the EPR has more to offer by going into the time domain. Now that, for those people who have listened to the NMR talks, for all of you, or Henrik's talk on Monday, gave an insight into pulsed NMR spectroscopy. And basically, to make the long story short, the same technique can be used also in EPR spectroscopy. So we're doing a time domain, pulsed excitation, and record the free induction decay. Keep going a little bit. And I'll give you one example. These are the photothermal refractive glasses. They are complicated compositions over here that are used by the Glebov group to produce optical devices. What's important here is there's some sodium fluoride crystallization happening that produces periodic structures that are important for optical elements. But this will only happen if the glasses contain some dopants here, like silver needs to be doped in there, cerium 3+, antimony 3+, and tin 2+. And so we used EPR spectroscopy to find out what the role of these dopants was. And to show you, we got some results for the initial stage. So basically, what we see here is a spectrum of the glass that has all these different elements plus all of these dopants. And this is the spectrum that you get of EPR spectroscopy. This was done by pulsed excitation while sweeping a magnetic field. It's called EDFS, electron detected field sweep, and basically allows you to record rather broad spectra that you would not normally be able to measure by continuous wave spectroscopy. You notice here, we do not do the field modulation in this case. You record the spectra directly in this way. And what you see, the experimental data comprise two components that correspond to magnetic hyperfine interaction with antimony 121 and 123 nuclei. Yeah? This antimony is one of these trace elements present in these glasses, we observe them here according to their natural abundances. 123 is spin 7/2, 121 is spin 5/2. These are the fitted line shapes of for these nuclei. And you can see on top of this, there's a broad component which arises from the cerium 3+, the rare earth ion. And then, when you anneal these glasses, the signal goes away. Yeah, so we must conclude that the antimony, the unpaired electron near the antimony, which would be an antimony 4+ species, yeah, is just an intermediate, and after annealing it disappears. Here we see the spectra, and basically allowed us to formulate a hypothetical mechanism. What's happening here? We have cerium 3+ that goes upon photothermal excitation to cerium 4+, and the one electron. That electron sits near the antimony, goes to an antimony, makes this antimony 4+ formally, and then this antimony 4+ stimulates nucleation of silver, and silver stimulates nucleation of sodium fluoride. So that was the conclusion from that EPR work done about 10 years ago. Yeah. Another effect I want to briefly mention is the electron spin echo envelope modulation. In this case, again, you do a pulsed excitation of the electron by stimulated echo, and you basically record the amplitude of the echo as a function of this time delay here. And it is both the nuclear hyperfine interaction and the dipolar interaction that causes this echo not to decay like a regular relaxation effect, but the decay is modulated. Yeah? And this modulation reveals, in certain cases that are important for the glasses, it reveals the proximity of nuclei. And so what you can do is you can strip off that decay, do a Fourier transform, And all the nuclei that are near the unpaired electron show up with their nuclear Zeeman frequencies. In this case, in this particular glass here, we were able to observe the boron nuclei near the, in this case, the dopant was ytterbium. So it was an ytterbium-doped yttrium aluminoborate glass, and we were able to prove the proximity of these boron nuclei. And so basically, this allowed us to develop a methodology for analyzing rare earth environments in some glasses. I think here we looked at fluoride phosphate laser glasses. And basically, you try to develop an NMR strategy for this. One way, of course, would be we cannot see with NMR, we cannot see the paramagnetic ions, but we can replace them by scandium and yttrium, which are diamagnetic, and get information from that. We can also look at the how the paramagnetic ion is affecting nuclei in their vicinity. That is, we're looking at the NMR spectra of constituent nuclei near the paramagnetic ion by using NMR, but we can also do it by doing EPR in using this electron spin echo envelope modulation. Yeah, and that was, and I'd like to basically conclude my talk with this last result here. Namely, we have here a series of fluoride phosphate glasses, and we were interested in whether it was fluoride or phosphate that were linking to the rare earth ion. And we did a series here of phosphorus and fluoride dopings. So the phosphate versus fluoride was changed. Yeah? And you can see here how the electron spin echo envelope modulation signals for phosphorus and for fluoride are changing in the relative intensity. Here, this is a pure fluoride glass. Here is a phosphate glass, a phosphofluoride glass that has both of them, and we see a gradual change in the contributions as you would expect. So what I want to say is NMR and EPR are really complementary. With NMR, we're looking at the short range order of the nuclei. We can get into the medium range order also, at least into the second coordination sphere by using this double resonance technique that Henrik talked about on Monday. So REDOR and REAPDOR. With EPR, we have additional information beyond the second coordination sphere using this electron spin echo envelope modulation effect. And of course, we're looking at the atom directly of the rare earth. We can analyze the situation based on G values and G tensor. In simple cases like copper, it's possible. Yeah, I'd like to thank, this is the last picture of the San Carlos group and a magnetic resonance group that I'm in. I'm very pleased to see that now Marcos and Henrik are carrying the ball further. And I'd like to thank everybody for the contribution and the many years that we worked here together on NMR and EPR of glasses. And again, the funding by CERTEF, FAPESP was very crucial for this, for building up this group. Thank you very much.
All right, we have time for a few brief questions.
So, hi, thanks very much for the talk. My name is Marcelo. I'm from SHOT and also a master's student at Federal University of San Carlos. This technique is very new to me, so maybe the question is a little bit obvious, but I was curious to know, when you say, for example, that relaxation can ruin or make some noise in the experiment, would it be possible to see the relaxation process like a quantitative or qualitative way? And would it change like the peak position, the high, the broad? Just, you know.
Right, right. Yes, no, good, very good question. Example, for instance, is titanium 3+. Many times you look for titanium in a glass and by EPR and you don't see it because the relaxation is too fast. It basically then broadens, it makes the signal so broad that it gets wiped out on the baseline. Then you need to cool down and slow down the relaxation. The relaxation time is highly temperature dependent for unpaired electrons, and so it may show up then at a certain temperature. So don't give up yet. And with the rare earths, I can tell you, you need to go close to helium temperature to see anything. Yeah, and there are techniques, more complex techniques, but pulse techniques that allow you to measure these relaxation times. So you can quantify. Yeah.
Anyone else? Or are you all starving? I guess it's up to you.
Okay, thank you very much, Helmut. Thank you very much, Jack, for chairing the morning session. I think it was very, very good. Just a brief announcement. Who are the Brazilians who live in São Carlos who know the ways to the restaurants? Please come here. Marcelo, Ricardo, Eduardo, are you going to eat here? Checking with your boss, right? I know. João Vitor, please come here. So we have to organize this a little bit. There are several restaurants nearby, but we cannot go all to the same restaurant. It'll be a mess. So please follow these guys. We have to split to different restaurants. I'll be here too. You can follow me too. And I think, Marcio, you're going with them, right? So this, I think we can go to 5 different restaurants. 5 different restaurants. So you have to follow one of these guys, okay, for lunch.
Tell them it's the vegetarian that wants to go with us because we're going to Mother Nature's restaurant, so it's more vegetarian style.
Well, in most places, there are plenty of salads. If you're a vegetarian, there's always salads, you know. There is a restaurant here inside the university. Where, Claudio, where is the cantina? Where? Okay, maybe. Henrik. Well, can you lead these people to the cantina? Yeah, just show them. So there is this free cantina with no the university restaurant. Yeah. Well, as he said, it's not the best food. It's university restaurant. It's free, so it's up to you. If you want a little bit better food, you have to pay a little bit, but you have your per diems. Second thing, Laurie will be here. Laurie will be here after lunch to sort out money problems. You know, maybe some of you still need to get some money. She'll be here in the afternoon. Finally, let's try to be back. Please try to be back by 1:30 or so. You have to hang your posters. You have to hang your posters. Hey?
They should put their posters there today during the lunch, you know?
Yeah.
So say to them.
Yeah. They'll come back earlier to hang the posters. Yes. Let me talk to. Hey, hi Doris. How are you? Let's try to get the session usually on time. Did you get my email?
Yes.
Yeah. You're